Listen carefully to this sound. It's not a soundtrack from a science fiction movie, not a digital glitch, and not something from our own world. It is the sound of a mystery echoing across the cosmos, a brief and incredibly powerful blast of radio energy that traveled for hundreds of millions of years before our telescopes finally caught it. This is a fast radio burst, one of the most bewildering and captivating phenomena in the entire field of modern astronomy. For decades, we've looked to the stars and seen a universe of predictable rhythms and constants, but these signals defy all that. They are cosmic shouts in the dark, brief, brilliant, and vanishing almost as soon as they appear, leaving behind more questions than answers and challenging our fundamental understanding of the universe itself. Welcome to a journey into the great unknown, to the very edge of our scientific understanding. We are about to explore 30 of the most profound, unexplained signals ever detected from the depths of our galaxy and beyond. Each one is a unique enigma, a cosmic event so powerful it can outshine entire galaxies for a few fleeting milliseconds. Some of these bursts are one-off explosions, cosmic singularities that flash and are never heard from again. Others are repeating, persistent signals that pulse with an eerie, unpredictable rhythm, almost as if they are sending a message. They arrive from random directions in the sky, their origins hidden in the vast, dark spaces between galaxies, and their sheer power defies easy explanation. What natural engine could possibly generate such immense energy and release it in a fraction of a blink? This is more than just a list of strange space events. It is a detective story on a galactic scale, a search for meaning in the noise. For every one of these 30 signals, brilliant minds have put forward theories that range from the known extremes of physics to concepts that sound like pure fantasy. Are we witnessing the violent death throes of exotic stars, the unimaginable power of colliding black holes, or something else entirely? Could some of these signals be evidence of advanced civilizations, technological signatures from beings so far beyond us that their very existence redefines our place in the cosmos? We will delve into the leading scientific ideas, weighing the evidence and the extraordinary possibilities, pulling back the curtain on one of the greatest scientific adventures of our time. So prepare to be amazed, to have your perspective shifted, and to look up at the night sky with a renewed sense of wonder, because we are about to uncover the secrets of these 30 unexplained galactic signals. Our journey into the unknown begins not with a complex modern detection, but with a discovery made in old data, a ghost from the past that had been waiting years to be noticed. This is the story of the Lorimer burst, officially catalogued as FRB 010724. It was 2007 when astronomer Duncan Lorimer and his student were sifting through archival observations from the Parkes radio telescope in Australia, data that was actually recorded back in 2001. They were looking for new pulsars, those rapidly spinning neutron stars, but instead they found something that defied all known categories. It was a single spike of radio energy, a blast that lasted just 5 milliseconds. To put that into perspective, in the time it takes you to blink, 200 of these bursts could have come and gone, but its brevity was matched by its sheer, staggering power. In those few thousandths of a second, this burst released more energy than our sun puts out over 30 years. The data pointed to an origin billions of light years away, far beyond our own Milky Way galaxy. This wasn't a local event, it was a scream from an unimaginably distant and ancient cosmos. The initial reaction in the scientific community was profound skepticism. Could this be real, or was it just some kind of terrestrial interference, a glitch from a passing satellite, or even a microwave oven in the observatory's kitchen? The fact that it was a one-off event, a singular pulse that never repeated, made it even harder to verify and study, but the evidence was compelling. The signal exhibited a telltale sign of a true cosmic traveler, an effect called plasma dispersion, where higher radio frequencies arrive at the telescope slightly before the lower ones. This happens because the waves have traveled through the sparse ionized gas that drifts between galaxies, and the amount of this dispersion confirmed the burst had journeyed across an epic intergalactic distance. The Lorimer burst forced astronomers to confront a new reality. It couldn't be explained by any known stellar object or event. Theories began to swirl around what kind of catastrophic event could be the source. Perhaps it was the final, dramatic collapse of a supermassive neutron star into a black hole. Maybe it was the merger of two incredibly dense stellar corpses like neutron stars. Some even ventured into more speculative territory, pondering if it was evidence of something entirely new, like a cosmic string undergoing a phase transition. This one signal, hidden in plain sight for years, single-handedly opened up an entirely new field of astrophysics. It was the first clue, the spark that ignited a global hunt to find more of these cosmic enigmas and to finally understand what in the universe could possibly be so loud, so fast, and so devastatingly powerful. While the Lorimer burst revealed a new class of cosmic explosion, our next signal presented an entirely different kind of puzzle, one that felt less like a natural catastrophe and more like a deliberate call. We travel back to a summer evening in 1977 to the Big Ear radio telescope at Ohio State University. This instrument was part of the early Search for Extraterrestrial Intelligence, or SETI, program, patiently scanning the sky for any sign of a signal that couldn't be explained by nature. On August 15th, the telescope's computer printed out long reams of data, columns of letters and numbers representing the strength of incoming radio waves. Days later, a volunteer named Jerry Amon was reviewing the printout, and his eye caught something that made him stop cold. Next to a string of characters from a specific region in the constellation Sagittarius, he saw a sequence so startling he circled it in red pen and wrote a single, now legendary word in the margin: "Wow." That circled sequence was 6 Equage 5. To understand why this was so shocking, you have to know what it represents. The Big Ear telescope measured signal intensity not with numbers but with a code. The numbers 1 through 9 were used, and then the alphabet from A to Z, with each letter representing a progressively stronger signal. Most of the printout was filled with spaces and the occasional number 1 or 2, the expected background noise of the universe. This sequence, 6EQUJ5, showed a signal that rose rapidly in strength, peaked at an intensity level of U, which is 30 times louder than the ambient cosmic static, and then faded away all over the course of 72 seconds. This precise duration is crucial because it's exactly how long a fixed, distant signal would take to pass through the Big Ear's stationary twin-beam telescope. It was the perfect match for a signal coming from interstellar space. It was also a narrowband signal, concentrated on one specific frequency, the hydrogen line at 1420 MHz. This is significant because hydrogen is the most common element in the universe, and many scientists had suggested it would be a logical, universal hailing frequency for any civilization attempting to make contact. It was as if the universe had answered the phone on the very line we had been listening to. The immediate and enduring mystery is that the WOW signal was never heard again. Despite numerous dedicated efforts to find it over the following decades, using far more sensitive equipment, the signal remained a singular, tantalizing event. This one-off nature is what fuels the debate and the fascination. The search for a plausible explanation has led scientists down many paths. Some proposed it was a signal bounced off a piece of space debris, perhaps a passing satellite or a bit of orbiting junk. The problem is that the frequency used is protected by international agreement. No earthly transmitters are supposed to broadcast on it, making a human-made source very unlikely. More recently, a theory gained some traction that the signal was caused by the hydrogen clouds surrounding a pair of comets that happened to be in that part of the sky at the time. However, this explanation has been largely refuted. Comets are not strong emitters at that specific frequency, and the comets in question weren't even in the telescope's field of view when the signal was detected. The very lack of a definitive natural explanation is what keeps the most profound possibility alive. Could the WOW signal have been a transient, one-time transmission from an advanced extraterrestrial civilization, a cosmic hello that flashed into our detection and then vanished forever into the void? It remains the gold standard, the benchmark against which all other potential SETI signals are measured, a permanent and powerful reminder that the question, "Are we alone?" is still very much open. Just when astronomers thought they were starting to understand fast radio bursts as singular, cataclysmic explosions, the universe delivered a curveball that redefined the entire mystery. The discovery came from the Arecibo Observatory in Puerto Rico, a giant dish nestled in a natural limestone sinkhole. There, in November 2012, a burst was detected and catalogued as FRB 121102. For years, it was just another data point, a one-off flash presumed to be like the Lorimer burst. But then, something extraordinary happened. In 2015, astronomers pointed Arecibo back at the same patch of sky and saw another burst. And then another. They realized that FRB 121102 was actively repeating, firing off multiple bursts in an unpredictable staccato rhythm. This wasn't a final death cry. This was an object with a persistent, volatile personality. It completely shattered the prevailing theory that all FRBs were caused by one-time, self-destructing events like neutron star mergers or stellar collapses. Whatever was creating these signals had to be able to survive its own outbursts again and again. Pinpointing the home of this repeater became the next great challenge and triumph. Using a coordinated array of the world's most powerful radio telescopes, scientists were able to triangulate its location with incredible precision. They found that it resided not in a large, stately spiral galaxy like our own Milky Way, but in a tiny, unassuming dwarf galaxy a staggering 3 billion light-years from Earth. This dwarf galaxy was a surprise in itself. It was a place of frantic star formation, a cosmic nursery churning out new stars at a furious rate. This environment provided a crucial clue. Such a place is rich in the raw materials needed to create the most extreme stellar objects in the universe, including the prime suspect for the repeating bursts, a magnetar. A magnetar is a type of neutron star, the super-dense core left behind after a massive star explodes in a supernova. But a magnetar is a neutron star on steroids, possessing a magnetic field so intense it's 1,000 trillion times stronger than Earth. These fields are under unimaginable strain, and they can occasionally snap and reconfigure in events known as starquakes, releasing titanic flashes of energy. The erratic, repeating pattern of FRB 121102 fits beautifully with the idea of a young, hyperactive magnetar, periodically cracking under the pressure and letting out a scream of radio waves. But the story doesn't end with a simple, solitary magnetar. The sheer rate of its repetitions, with hundreds of bursts detected over the years, suggests this object might be in a particularly dynamic and fuel-rich environment. One compelling theory is that this magnetar is not alone. It could be orbiting a supermassive black hole or be nestled deep within a dense nebula, a cloud of gas and dust left over from the supernova that created it. In this scenario, the magnetar's powerful magnetic field acts like a cosmic paddle, stirring up the surrounding material. As this gas and dust are whipped into a frenzy, they could periodically collapse onto the magnetar's surface, triggering the intense bursts of radio energy we detect. This would be like throwing logs on a fire, providing a recurring fuel source for the explosions rather than relying solely on internal starquakes. Another, more speculative idea involves a magnetar that is also a pulsar, a neutron star that spins rapidly, beaming energy like a lighthouse. If its rotational energy and its magnetic energy were to interact in just the right chaotic way, it could generate these powerful, repeating signals. The existence of this one repeating source opened up an entire new landscape of theoretical physics, transforming FRBS from simple mysteries into complex dynamic systems that we are only just beginning to comprehend. This dwarf galaxy, located an incredible 3 billion light-years away, became far more than just a cosmic address. It transformed into a key character in the story. You might picture our own majestic Milky Way, a vast, stately spiral with defined arms, a calm central bulge, and a relatively settled pace of stellar life and death. The home of FRB 121102 is the complete opposite. It's a diminutive, chaotic, and incredibly fertile star-forming galaxy. Imagine a bustling, crowded metropolitan downtown under constant construction, compared to a quiet, sprawling suburban neighborhood. That's the difference. In this dwarf galaxy, stars are being born at a frantic, almost violent rate. Vast clouds of gas and dust are collapsing under their own gravity, igniting into brilliant, short-lived massive stars. This frenetic environment is a crucible for cosmic drama, and it provides the perfect breeding ground for the kinds of extreme stellar objects that could produce repeating fast radio bursts. The significance of this location cannot be overstated. It immediately ruled out a whole class of potential explanations. If the signal had originated from an old, evolved elliptical galaxy, a place where star formation ceased billions of years ago, populated mostly by long-lived, smaller stars, then theories involving cataclysmic, one-off events from ancient stellar remnants might have held more weight. But this specific, youthful, and turbulent dwarf galaxy pointed directly towards objects associated with recent, violent stellar death. It's an environment rich in the necessary ingredients, massive stars that live fast and die young, leaving behind the most exotic and volatile stellar corpses in the universe. This host galaxy was the crucial piece of evidence that strongly supported the leading suspect, a magnetar. A magnetar is the collapsed core of a truly massive star that has undergone a supernova explosion. In a calm galaxy, a neutron star might just spin down quietly over eons. But born in this frantic stellar nursery, a neutron star is likely to be spun up and magnetized to an insane degree, becoming a magnetar. The constant turmoil of the surrounding environment, with its shock waves from nearby supernova and intense radiation from brilliant young stars, could easily trigger the immense starquakes on a magnetar's surface that are thought to power these bursts. It's a perfect match, a volatile engine placed in a volatile neighborhood, creating the perfect conditions for repeated, explosive outbursts. Furthermore, this host galaxy provided a plausible explanation for the sheer persistence of this particular repeater. While internal starquakes on an isolated magnetar could explain some bursts, the hundreds of signals from FRB 121102 suggest an external fuel source. In a dwarf galaxy teeming with star formation, the magnetar could be plowing through the dense, leftover debris of the supernova that created it, a cloud known as a nebula. As the magnetar moves, its unimaginably powerful magnetic field could interact with this surrounding material, pulling it in and causing it to crash onto the star's surface in violent, episodic avalanches. Each avalanche would release a tremendous amount of energy, manifesting as the fast radio bursts we detect. This scenario paints a vivid picture, not just a solitary magnetar cracking under pressure, but an active, dynamic system, a cosmic engine fed by the rich resources of its chaotic home. This one location, this tiny, turbulent galaxy, gave astronomers their first real environmental context for these mysterious signals, turning a point of light into a living, breathing cosmic ecosystem, and providing a fundamental framework for understanding where else we should be looking for these brilliant, repeating cosmic beacons. Just as we were getting used to the idea of unpredictable, sporadic repeaters, the universe unveiled a signal with a cosmic clockwork precision that left astronomers utterly astonished. This is the story of FRB 180916, a discovery that added a whole new layer of profound mystery to the fast radio burst saga. Detected by the CHIME telescope in Canada, this source didn't just repeat, it did so on a strict, predictable schedule. For roughly 4 days, it would fire off bursts, sometimes several per hour, and then it would fall completely silent for the next 12 days. This 16.35-day cycle was a game-changer. It was the first time we had found a fast radio burst with a confirmed, regular periodicity, a rhythm to the cosmic noise. This wasn't just a clue, it was a giant, flashing arrow pointing directly at the mechanism powering these incredible emissions. The existence of such a stable cycle immediately narrows down the possible scenarios dramatically. A one-off cataclysm like a star collapsing or two objects merging is ruled out entirely. You can't have a predictable schedule for a single destructive event. This had to be the signature of a system, an ongoing celestial dance where geometry and motion create the regular pattern we observe. The most compelling explanation, and the one that fits the data most elegantly, involves a binary system, two objects locked in a gravitational embrace. In this model, the source of the bursts is a highly magnetized neutron star, a magnetar. But this magnetar isn't alone, it's orbiting another, much more massive object. That companion could be another neutron star, or more likely, a massive, hot, and young O or B-type star, the kind that lives fast and dies young. So how does this binary dance create the on-again, off-again signal? The key lies in the magnetar's orbit. Imagine it moving around its companion on a slightly elliptical path. For about 4 days of its 16-day orbit, the magnetar is in a position where its powerful beams of radio emission can sweep across our line of sight here on Earth. We see this as the active window, but then for the remaining 12 days, the geometry of the system changes. During this period, the companion star itself gets in the way. A massive star like this doesn't have a calm surface. It constantly blows off a powerful stream of charged particles, a stellar wind that forms a vast, dense cloud around the entire system. As the magnetar moves behind this cloud from our perspective, the stellar wind acts like a thick fog, absorbing or scattering the radio waves before they can ever reach us. The signal isn't stopping, it's just being blocked, effectively placing a cosmic curtain in front of the source for most of its orbital period. Another fascinating variation on this theme involves the companion star having a vast disk of material around it, perhaps leftover debris from its formation or material being pulled from its outer layers. In this scenario, the magnetar's beams might be constantly firing, but we only detect them when its orbit carries it above or below the plane of this opaque disk, allowing the signals a clear path out of the system. The regular periodicity, then, is simply the clock of the orbital motion, with the active window representing the brief moments of clear transmission. This model is so powerful because it not only explains the when of the bursts, but also gives us a way to estimate the properties of the objects involved. The 16-day period suggests an orbital separation of hundreds of millions of kilometers, and the 4-day active window tells us about the size and density of the stellar wind or disk that acts as the blocker. This transforms the fast radio burst from a mere flash in the dark into a sophisticated astrophysical laboratory, allowing us to probe the conditions around some of the most extreme objects in the cosmos from a distance of 500 million light-years. The discovery of this periodic rhythm showed us that the engines behind these bursts can be intricate, choreographed systems, making the mystery even more complex and beautiful than we ever imagined. If the 16-day period of FRB 180916 felt like a predictable cosmic clock, then our next signal is its complete opposite, a source of relentless, chaotic radio chatter that refuses to be ignored. This is FRB 190520, a repeating burst discovered by the 500-meter aperture spherical telescope, or FAST, in China. It was immediately notable for its sheer hyperactivity, bursting frequently and with incredible intensity. But its true distinction, the feature that truly set it apart and sent theorists scrambling, was discovered when astronomers aimed other telescopes at its location. They found that between its brilliant millisecond flashes, the source never actually went quiet. It was co-located with a compact, persistent radio source, a constant, steady hum of radio waves emanating from the exact same point in space. To understand why this is such a revolutionary discovery, you need to grasp what a persistent radio source is in this context. Most cosmic objects we detect in radio waves are either transient, like the fast radio bursts themselves, or they are steady emitters, like the constant glow from the hot gas in a distant galaxy's core. Finding a source that is both a steady, unwavering radio hum punctuated by violent, ultra-bright flashes is incredibly rare. It's like listening to a Geiger counter that has a continuous, low-level tick, but then, without warning, it erupts into a deafening roar before settling back down to that same steady tick. This combination tells us that we are not just looking at a single, isolated object having occasional fits. We are looking at an entire system, an energetic environment where a powerful central engine is continuously pouring energy into its immediate surroundings, and that environment is responding by glowing constantly in radio waves. The leading theory that elegantly explains this entire bizarre package is that we are witnessing a cosmic infant, a newborn magnetar that is still in its natal cocoon. When a very massive star explodes as a supernova, it doesn't always completely blow itself to smithereens. The core of the star can collapse under its own gravity to form an incredibly dense neutron star. And if that neutron star is born spinning furiously and with an unimaginably strong magnetic field, it becomes a magnetar. In this youthful phase, the magnetar is not alone. It is still enveloped by the expanding cloud of debris from the supernova explosion that created it, a hot, dense shell of gas and dust known as a supernova remnant. This is the key to the mystery. The newborn magnetar acts like a powerful engine, and the supernova remnant is the fog that surrounds it. The persistent radio hum comes from this surrounding nebula. The magnetar's intense magnetic field and powerful winds of charged particles constantly slam into the inner walls of the supernova remnant. This interaction energizes the gas, causing it to glow brightly in radio wavelengths, creating the steady source we detect. It's a cosmic feedback loop. The magnetar feeds energy into the nebula, and the nebula responds by shining. Now, imagine that this young magnetar is also prone to the same violent starquakes that we suspect power other fast radio bursts. When one of these dramatic crust-shaking events occurs on the neutron star's surface, it releases an immense, focused blast of energy. That blast travels outwards, but it doesn't travel through empty space. It has to punch its way through the very same dense, glowing nebula that is responsible for the persistent radio source. This interaction between the sudden blast and the surrounding cloud could be what shapes and amplifies the signal into the incredibly bright, millisecond duration fast radio burst we eventually detect. The persistent source is the background state of the system, while the bursts are the spectacular fireworks going off inside it. This young magnetar model is powerfully compelling because it also explains another strange property of FRB 190520. Measurements of its signal showed an unusually high amount of dispersion, suggesting it was embedded in an extremely dense environment, exactly what you would expect from a supernova remnant that hasn't had time to dissipate and thin out. This source presents a snapshot of a brief, tumultuous phase in a magnetar's life. In a few tens of thousands of years, the supernova remnant will expand and fade away. The persistent radio source will vanish, and all that might be left is an older, more isolated magnetar that only occasionally flashes. FRB 190520 gives us a front-row seat to the stormy childhood of one of the universe's most extreme objects, showing us that the environment around the central engine is just as important as the engine itself in creating the mysterious signals that captivate our curiosity. While individual discoveries like the repeating and periodic bursts were rewriting the rulebook, a quiet revolution was taking place in the mountains of British Columbia, an engineering marvel that would transform this field from a niche hunt into a data-rich science. This is the story of the Canadian Hydrogen Intensity Mapping Experiment, or CHIME. Unlike the colossal, moving dish of Arecibo or the steerable parabolas of other observatories, CHIME looks almost alien in its design. It consists of 4 massive, stationary half-pipe cylinders, each as long as a city block and lined with over 1,000 antennas. It has no moving parts. Instead of pointing at a single spot, it simply stares fixedly at the sky as the Earth rotates, using sophisticated digital signal processing to act as a gigantic cosmic drift net, capturing whatever radio waves pass overhead. This unique design gives it an unparalleled field of view, allowing it to scan the entire northern sky every single day. Where a conventional radio telescope might study one star or galaxy for hours, CHIME sees a vast swath of the universe all at once, making it the perfect instrument for catching fleeting, unpredictable events like fast radio bursts. The impact of this new tool was immediate and explosive. Before CHIME came fully online, the entire catalogue of known FRBs numbered less than 100, each one a hard-won discovery. Within just its first year of operation, CHIME was discovering them by the dozens every month. Today, it has detected thousands of these events. This torrent of data was the critical shift the field needed. It moved scientists from the era of the anecdote, painstakingly analyzing 1 or 2 peculiar signals, into the era of statistics, where they could finally study FRBs as a population. It's the difference between a biologist studying a single, unique butterfly and having a vast collection of butterflies from all over the world, allowing you to see patterns, identify different species, and understand their distribution and life cycles. With thousands of bursts to analyze, astronomers could begin to answer fundamental questions. How common are repeaters versus one-off bursts? What is the true range of their energies? How are they distributed across the sky and across cosmic time? This statistical power led to a cascade of profound discoveries. CHIME didn't just find more bursts, it found more kinds of bursts. It was CHIME that confirmed the stunning 16-day periodicity of FRB 180916, revealing the clockwork nature of some of these systems. It discovered a vast number of new repeaters, confirming that repeating sources are not a bizarre fluke but a significant subclass of FRB, likely powered by persistent engines like magnetars. It also detected bursts of astonishingly low frequency, pushing the boundaries of what we thought was physically possible for these signals to travel through space without being absorbed. Each new detection added another data point, allowing scientists to categorize FRBs based on their dispersion, their burst width, their spectral structure, and their repetition patterns. This classification is the first step toward understanding the different physical engines that must be at work. Some bursts are likely from young magnetars in turbulent nurseries, while others with clean, one-off profiles might still be the signature of final, catastrophic mergers. CHIME data provides the map that guides theorists toward the correct explanations. Beyond just counting and categorizing, CHIME's true revolution lies in its potential for cosmic cartography. Every single fast radio burst it detects carries within its signal a hidden measurement of the cosmos. The smear of its frequencies, the dispersion measure, tells us the total amount of ionized material its light has passed through on its journey to Earth. With thousands of these measurements from bursts located at different distances across the universe, astronomers can begin to build a three-dimensional map of the otherwise invisible cosmic web, the vast, diffuse filaments of gas that stretch between galaxies. This is like turning on a light in a dark, foggy room and using the thousands of tiny water droplets to see the structure of the fog itself. By tracing where the missing normal matter of the universe is located, FRBs have become one of the most promising tools in modern cosmology, and it is the CHIME telescope, with its relentless daily harvest of signals, that has made this ambitious new science a tangible reality. It transformed FRBs from celestial oddities into standard candles and mapping tools, proving that the greatest mysteries, when studied in sufficient numbers, can begin to reveal the fundamental structure of the cosmos itself. For years, the hunt for the source of fast radio bursts was a search for ghosts in the deepest, darkest extragalactic voids, events so distant and powerful they seemed to belong to another reality entirely. Theorists had their prime suspect, the magnetar, but it was a hypothesis built on inference and circumstance, not direct proof. Then, in April 2020, the case broke wide open, not from a galaxy billions of light years away, but from a known object right here in our own cosmic backyard. The star of this breakthrough is a magnetar known as SGR 1935+2154, located about 30,000 light-years away in the constellation Vulpecula. This particular object had been known to astronomers for years as an active soft gamma repeater, prone to occasional outbursts of high-energy X-rays and gamma rays. But on April 28th, it did something completely unprecedented. It began with a violent episode of X-ray bursting, a sign that the magnetar was undergoing a major starquake, its incredibly rigid crust cracking under the strain of its own magnetic field. Then, in the middle of this activity, two of the world's most sensitive radio telescopes, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, and the Survey for Transient Astronomical Radio Emission 2, or STARE-2, in the United States, caught an extraordinary signal. From the precise location of SGR 1935+2154, a brilliant millisecond duration burst of radio waves erupted. This was not a mere pop or crackle. It was a blast that, for a single, fleeting moment, outshone every other radio source in the entire galaxy. The energy released was staggering, millions of times brighter than any radio burst ever before detected from a known object within the Milky Way. It was a true FRB in every way except one. This galactic FRB was a crucial piece of the puzzle precisely because of its relative weakness. While it was the most powerful radio burst ever seen from inside our galaxy, it was also thousands of times fainter than the typical extragalactic fast radio bursts we detect from other galaxies. This wasn't a contradiction, it was the final, confirming piece of evidence. It bridged the vast energy gap that had long perplexed scientists. Here was the smoking gun, proving unequivocally that magnetars are indeed capable of producing the specific type of explosive radio emission we classify as a fast radio burst. The reason the bursts from distant galaxies are so much brighter is simply a matter of scale. The magnetars there must be younger, more magnetized, or operating in even more extreme environments, allowing their outbursts to reach the colossal energies needed to travel across intergalactic space and still be detected by our telescopes. The event from SGR 1935+2154 was the local, scaled-down version, the definitive proof of concept happening right next door. This single detection transformed the entire field of FRB research. It moved the magnetar model from a compelling front-runner to an established, verified source for at least a significant population of these signals. The event also provided an invaluable, close-up laboratory to study the mechanics of the burst itself. The simultaneous detection of X-rays and radio waves was a critical detail. It strongly suggests that the initial trigger is a catastrophic rearrangement of the magnetar's magnetic field, a starquake, that unleashes a firestorm of high-energy radiation. This initial explosion then interacts with the incredibly dense, magnetized plasma surrounding the star, and it is this complex interaction that somehow channels a portion of the energy into an intense, coherent beam of radio waves. We were no longer just guessing at the process, we were witnessing its different stages unfold in real time from a known object. This galactic magnetar didn't just solve one mystery, it gave astronomers a detailed blueprint for how to interpret the thousands of more distant, more powerful bursts, confirming that we are, in many cases, listening to the cosmic tantrums of the universe's most magnetic and temperamental stellar corpses. Yet for all the fascinating complexity of repeaters, they represent only a fraction of the story. The vast majority of fast radio bursts, over 95% of the thousands now detected, are one-off events, cosmic flashes in the pan that scream into existence and are never, ever heard from again. These singular bursts present a fundamentally different kind of scientific challenge. A repeater offers multiple chances for observation. You can point the world's most powerful telescopes at its location and wait, gathering more data with each new flash. But a one-off burst is a ghost. It gives you a single, fleeting data point, a brief spike of radio energy from a random point in the sky, and then vanishes forever into the silence. Studying these is like a detective arriving at a crime scene after the fact, with only a single, blurry photograph as evidence and trying to reconstruct the entire event. The very nature of their one-and-done character is ironically the most important clue we have. It strongly suggests that whatever event caused the burst was so profoundly catastrophic that the source was completely and utterly destroyed in the process. The engine didn't just shut off, it exploded. This leads us to theories that are necessarily more violent and final than the persistent activity of a magnetar. One of the most compelling candidates is the cosmic collision of two neutron stars. Imagine these two incredibly dense stellar corpses, each one a city-sized object with more mass than our Sun, locked in a final, decaying orbit. As they spiral inward over millions of years, they rip each other apart with immense tidal forces before finally smashing together in an event of almost unimaginable violence. This merger is known to create a spectacular flash of light across the electromagnetic spectrum, a kilonova, and is also the source of the gravitational waves we can now detect. The leading hypothesis is that in the chaotic aftermath of this collision, as a new black hole is born or a hypermassive neutron star briefly forms, the surrounding magnetic fields can be wound up to incredible intensities. In a fraction of a millisecond, these fields could snap and reconfigure, launching a blisteringly fast and energetic shockwave that manifests as the single, brilliant radio burst we detect. The event is so final that the system capable of producing such a signal is simply gone. An even more exotic and dramatic possibility is a phenomenon known as a blitzar. This theory begins with a particularly massive neutron star, one that is already spinning at a significant fraction of the speed of light. This rapid rotation is what's keeping the star from immediately collapsing under its own immense gravity. It's like a cosmic merry-go-round with centrifugal force fighting a constant battle against gravity. But neutron stars are not perpetual motion machines. They gradually lose rotational energy, bleeding it off into space as winds and radiation. The blitzar scenario proposes that one of these massive, spinning neutron stars finally spins down to a critical point. The centrifugal support vanishes almost instantly and gravity wins. In a breathtakingly sudden event, the entire neutron star collapses directly into a black hole. According to the laws of physics, the star's incredibly powerful magnetic field cannot cross the boundary of the newly formed black hole's event horizon. It is, in a sense, left outside, disconnected from its source. This orphaned magnetic field, containing a colossal amount of pent-up energy, has nowhere to go. In an instant, it collapses in on itself, and all of that stored magnetic energy is released in a single, coherent, and devastatingly powerful blast of radio waves, a fast radio burst. The moment the burst is emitted, the magnetic field is gone, and all that remains is a newborn, silent black hole. It is the ultimate one-off event, the final death cry of a star that was living on borrowed time. Of course, we also cannot ignore the most familiar of cosmic catastrophes, the supernova. While a typical supernova from a massive star doesn't produce the specific radio signature of an FRB, astronomers are exploring the possibility of particularly extreme variants. One such candidate is the superluminous supernova, an explosion that can be up to 100 times brighter than a normal supernova. The engine for such an incredible release of energy is still debated, but it may involve a central magnetar dumping its rotational energy into the expanding stellar debris. It's plausible that in some rare cases, the birth of the magnetar itself, or a subsequent shock wave interacting with dense material ejected just before the explosion, could produce a brief, ultra-luminous radio burst just before the longer-term supernova glow becomes visible. Another, even more speculative idea involves the death of a very first generation of stars in the universe, known as population 3 stars. These hypothetical behemoths were many hundreds of times more massive than our Sun, and are thought to have ended their lives in utterly violent pair instability supernova that completely obliterated the star, leaving no remnant behind. The shockwaves from such a primordial cataclysm occurring in the early, pristine universe could potentially have generated a singular, extraordinarily powerful radio blast that has been traveling through space for billions of years. The challenge with all these one-off theories is connecting the model to the single, pristine data point. Without a repeating source to confirm the nature of the engine, astronomers must rely on statistical arguments, comparing the rates of these catastrophic events across the universe to the rates of detected one-off FRBs, slowly building a case for which cosmic disaster is the most likely culprit for the silent majority of these brilliant, self-destructing signals. This relentless search for origins brings us to the very edge of theoretical astrophysics, where we must grapple with cosmic events of almost unimaginable finality. For the one-off fast radio bursts, the leading theories are not about objects that survive their outbursts, but about systems that are utterly and completely destroyed in one glorious, catastrophic instant. The sheer power required for a single burst to be visible across billions of light-years points to engines that are, by their very nature, self-annihilating. Let's explore two of the most compelling and violent scenarios that could be the source of these cosmic last words. First, consider the fate of two neutron stars locked in a final, deadly dance. A neutron star is the collapsed core of a massive star, an object so dense that a single teaspoon of its material would weigh billions of tons. Now picture two of these incredible objects orbiting one another. Over countless millennia, they lose energy, slowly spiraling closer and closer together. In the final moments before they collide, their orbital period accelerates to a blur, and the tidal forces between them become so extreme that they begin to rip each other apart. When they finally merge, the impact is more violent than any supernova. The collision creates a ferocious fireball of heavy elements like gold and platinum, and for a brief instant may form a hyper-massive neutron star, an object so heavy it is teetering on the very brink of becoming a black hole. It is within this maelstrom of newborn matter and unimaginable density that the conditions for a fast radio burst could arise. The magnetic fields of the two original stars are tangled, amplified, and wound up to intensities that defy comprehension. In a flash, these fields can snap and reconnect, launching a shockwave that propagates through the surrounding plasma at nearly the speed of light. This shockwave, a single pulse of coherent radio energy, is the fast radio burst we detect. A millisecond later, the hypermassive neutron star itself collapses into a black hole, and the entire system is gone. All that remains is the brief echo of its death, a radio signal traveling through the void for eons. An even more exotic and dramatic possibility is a phenomenon known as a blitzar. This theory begins with a neutron star that is born with a secret flaw. It is just a little too massive to be stable in the long term. For a time, it cheats death. Its rapid rotation provides an outward centrifugal force that counteracts the inward pull of its own immense gravity, preventing an immediate collapse. This star is living on borrowed time, spinning like a frenetic top to keep itself from being crushed into a black hole. But neutron stars gradually slow down. They bleed rotational energy into space through their powerful magnetic fields and particle winds. The Blitzar scenario proposes that when one of these overly massive neutron stars finally spins down to a critical threshold, the centrifugal support vanishes in an instant. Gravity, patient and relentless, wins the battle. In a breathtakingly sudden event that takes less than a millisecond, the entire star collapses directly into a black hole. Here's where the physics gets truly fascinating. According to our current understanding, the magnetic field of the neutron star cannot cross the boundary of the newly formed black hole's event horizon. It is, in a sense, severed from its source, left orphaned in space. This magnetic field, which was wrapped tightly around the star, contains a staggering amount of pent-up energy. With the star gone, the field has nothing to hold it together. It collapses in on itself, and in that final, coherent implosion, all of its stored magnetic energy is converted into a single, devastatingly powerful blast of radio waves. It is the ultimate one-off event, the death of a star and the simultaneous death of its magnetic field, releasing its entire lifetime of stored energy in one brilliant, final farewell before the silence of the black hole reigns forever. Just as astronomers were building confidence in their ability to identify genuine cosmic bursts, the field was rattled by a series of baffling signals that seemed to mock their efforts. These were the peritons, named after the mythical winged stag that casts a human shadow. The name was chillingly apt, as these signals had all the hallmarks of genuine fast radio bursts. They were brief, dispersed, and incredibly bright, but they cast a shadow of a very earthly origin. For years, they created a major headache, blurring the line between profound cosmic discovery and mundane human activity. The mystery centered once again on the Parkes Radio Telescope in Australia. This iconic dish was detecting these periton signals, but with a bizarre and crucial difference. They were being picked up across multiple beams of the telescope's receiver simultaneously. A genuine cosmic source, trillions upon trillions of kilometers away, is so distant that it acts like a point of light. It will only register in one very specific beam of the telescope. A signal appearing in multiple beams at once is a classic signature of a local source, something either on the ground or very close to it, flooding the entire site with radio noise. The hunt for the culprit became a comedic yet scientifically rigorous detective story. Astronomers systematically eliminated every possible source. Could it be aircraft, satellite reflections, or perhaps lightning from a distant storm? They checked and double-checked, but the peritons remained stubbornly elusive. The breakthrough finally came when a clever researcher noticed that these mysterious signals only seemed to occur during daylight hours, and specifically around lunchtime. This pointed the finger squarely at the observatory's staff kitchen. The team installed a radio monitor right next to the microwave oven and began a new set of experiments. They discovered that if someone heated their lunch and then, in a moment of impatient hunger, opened the oven door a fraction of a second before the timer had fully finished and shut off the magnetron, the device that generates the microwaves, a brief, powerful burst of radiation would escape. This blast at 2.4 GHz would then ricochet off the metal structures of the observatory and up into the giant dish of the telescope itself. The telescope, designed to catch the faintest whispers from the cosmos, would faithfully record this man-made blast, and its signal processing software would interpret the reflection's journey through the atmosphere as dispersion, making it look, for all intents and purposes, exactly like a fast radio burst from deep space. The cosmic mystery had been solved, and the culprit was a ham and cheese sandwich. This episode, while humorous in hindsight, served as an absolutely critical lesson for the entire field of radio astronomy. It was a powerful and humbling reminder that our quest to understand the universe is always filtered through a layer of our own human-made noise. The Puritan controversy forced a major overhaul of observational protocols and data analysis techniques. Astronomers realized they needed much stricter vetting criteria. A key rule was established: for a signal to be considered a genuine candidate for an extragalactic fast radio burst, it must be detected by only a single beam of a multi-beam receiver, confirming its point-like origin. Furthermore, the practice of cross-referencing detections became standard. If a signal was picked up by the Parkes telescope, for instance, it now had to be verified by another, completely independent radio telescope located hundreds of kilometers away. If both dishes saw it, it was cosmic. If only one saw it, it was likely local interference. This simple but effective protocol instantly weeded out future Puritan-like false alarms and gave the entire community immense confidence in subsequent discoveries, like the repeating and periodic bursts, whose cosmic origins were confirmed by this very multi-telescope verification process. The Puritans, in the end, were not a failure of science, but a demonstration of its self-correcting nature. By diligently chasing down a false signal, astronomers made their tools sharper and their conclusions far more robust, ensuring that the next time a brilliant millisecond flash appeared in their data, they could look up at the stars with much greater certainty. Just when a clear pattern seemed to be emerging, with fast radio bursts appearing exclusively in youthful, chaotic dwarf galaxies, the cosmos delivered another stunning surprise that forced scientists to question their assumptions all over again. This brings us to Signal 13, a burst known as FRB 20201124A, which was traced back to a host galaxy that is the polar opposite of everything we had come to expect. This wasn't a small, blue, star-forming dwarf. It was a massive, mature elliptical galaxy, a cosmic retirement home for stars. These galaxies are often described in astronomical circles as red and dead. They are vast, smooth, and featureless collections of ancient red stars where the frenetic party of star formation ended billions of years ago. The gas and dust needed to make new stars has long since been used up or blown away, leaving a quiet, settled population of aging stellar citizens. Finding a fast radio burst, an event we strongly associate with the violence of youthful stellar death, in such a serene and ancient environment was like finding a newborn baby in a quiet library for senior citizens. It simply did not fit the established narrative. This discovery immediately sparked a fascinating debate and opened up entirely new theoretical pathways. If magnetars are born from the explosive deaths of massive, short-lived stars, how could one possibly exist in a galaxy that hasn't formed such a star for eons? The leading explanation proposes a scenario of cosmic patience on an almost unimaginable scale. It's possible that the magnetar that produced this burst wasn't young at all, but was instead an ancient stellar remnant that had been lying in wait for billions of years. Imagine a neutron star that was born during the last great burst of star formation in that elliptical galaxy, perhaps 10 billion years ago. For all that time, it spun quietly in the darkness, its internal structure under immense strain from a powerful, slowly decaying magnetic field. Theorists suggest that such an old magnetar could eventually reach a tipping point. The constant stress of its own magnetism could cause its solid crust, a material far denser than any on Earth, to suddenly and catastrophically fracture in a final, tremendous starquake. This single, delayed shattering would release the pent-up energy of billions of years, producing the fast radio burst we detected. In this model, we are not witnessing a recent death, but rather hearing the long-delayed final echo of a star that died when the universe was young. Another compelling theory challenges the very notion of elliptical galaxies being completely dead. While it's true that their galaxy-wide star formation has ceased, they are not entirely sterile. Deep within their vast spherical confines, there could be small, hidden pockets of residual gas that have, against all odds, managed to cling together. Under the right conditions, this gas could collapse and form a sparse, late-generation wave of star birth. This wouldn't be the dramatic, large-scale star formation seen in dwarf galaxies, but rather a faint, final whisper of stellar creation. It is entirely plausible that in one of these isolated pockets, a massive star could have formed relatively recently, perhaps only a few tens of millions of years ago, and lived out its short, violent life, culminating in a supernova that left behind a brand new, and therefore highly active, magnetar. This youthful engine, hidden within the ancient body of the elliptical galaxy, would then be fully capable of producing the kind of violent outbursts we associate with fast radio bursts. This theory suggests we may need to revise our view of these red and dead galaxies, seeing them not as entirely dormant, but as places that can still experience the occasional, localized stellar firework. The implications of this single detection from an unexpected location are profound. It strongly suggests that the engines powering fast radio bursts are not a one-size-fits-all phenomenon. We may be looking at multiple populations of sources. One population, the repeaters, are likely the young, volatile magnetars born in the vibrant stellar nurseries of dwarf galaxies. Another population, the one-off bursts, could be a mixed bag. Some might be from catastrophic mergers in spiral galaxies, while others, like this one, could be the final death spasms of immensely old magnetars in elliptical galaxies, their signals representing the last chapter in a stellar life story that began before our own planet even existed. This discovery beautifully illustrates that the universe always has more complexity to reveal, ensuring that the mystery of these brilliant cosmic signals continues to deepen and evolve with every new detection. While we have been focusing on the sources of these bursts, the signals themselves carry hidden messages about the vast, empty expanses they have crossed. This brings us to a crucial concept that transforms these bursts from mere flashes into cosmic measuring tapes: the dispersion measure. Picture a fast radio burst as a chorus of different voices, all singing the same note but at different pitches, from a deep bass to a high soprano. If this chorus traveled through a perfect vacuum, all the voices would arrive at your ear at exactly the same time. But space is not a perfect vacuum. It is filled with a sparse, invisible fog of ionized gas, atoms that have been stripped of their electrons. This fog, known as plasma, has a peculiar effect on radio waves. The higher frequency waves, the sopranos, travel through it a little bit faster than the lower frequency bass notes. As a result, over an immense intergalactic journey, the brief, sharp burst becomes smeared out. The high notes arrive at our telescopes first, followed a few milliseconds later by the low notes. This time delay is the dispersion measure, and it's a direct count of the total number of free electrons the signal has encountered on its path to Earth. It's like the burst collects a ticket for every mile of fog it travels through, and by measuring the smearing, we can read that ticket and know exactly how much material it passed. Now consider the implications of signals with exceptionally high dispersion measures. These are the bursts that have endured the longest journeys through the cosmic fog, suggesting they come from the most distant reaches of the observable universe. Some of these high dispersion signals are so extreme that they challenge our models of the cosmos. They appear to have traveled through more ionized material than our standard models of the universe's structure predict should exist along their line of sight. This presents two thrilling possibilities. The first is that these bursts are truly primordial, originating from the universe's infancy, perhaps just a billion years after the Big Bang. At that time, the universe was smaller, denser, and filled with a hotter, more ionized plasma. A burst from that era would have to fight its way through an incredible thickness of this early cosmic soup, resulting in the massive dispersion we measure. The second possibility is that the burst didn't just travel through the general intergalactic medium, but also passed through an exceptionally dense and turbulent environment near its source, like the thick heart of a galactic nucleus or the dense shell of a supernova remnant, adding a huge local contribution to its dispersion ticket before it even began its long intergalactic voyage. What began as a confounding property of these signals has now been flipped on its head, turning a mystery into one of the most powerful tools in modern cosmology. For decades, astronomers have struggled to account for all the normal matter, the atoms and ions, that theories of the Big Bang predict should exist. A significant portion of it seemed to be missing, hidden in the dark, vast spaces between galaxies. Fast radio bursts, especially those with accurately located host galaxies and known distances, are the perfect solution. We can think of them as cosmic dipsticks. By comparing the dispersion measure, the total amount of stuff the signal traveled through, with the known distance to the host galaxy, astronomers can measure the average density of the faint, ionized plasma in the cosmic web. Each burst gives us a single, precise measurement along one specific sightline through the universe. As we collect more and more of these measurements from bursts at different distances and in different directions, we can begin to build a three-dimensional map of this otherwise invisible material. We are essentially using these brilliant flashes to illuminate the shadowy architecture of the cosmos, weighing the missing matter that has eluded us for so long. The very property that made these signals so puzzling, their smeared-out arrival, has become their greatest gift, allowing us to use them as probes to chart the distribution of the universe's fundamental building blocks and finally solve one of cosmology's most persistent missing matter mysteries. Now, let's journey into one of the most exotic and mind-bending theories proposed for these signals, a concept that connects the mystery of fast radio bursts to the even grander cosmic puzzle of dark matter. This explanation doesn't rely on neutron stars, magnetars, or stellar collisions at all. Instead, it ventures into the realm of hypothetical physics and points toward an object that has never been directly observed, an action star. To understand this, we first have to talk about actions themselves. Actions are hypothetical elementary particles, originally proposed to solve a subtle problem in particle physics concerning the strong nuclear force. They are theorized to be incredibly light, trillions of times lighter than an electron, and to interact only very weakly with normal matter. Because of these ghostly properties, actions have become a leading candidate to explain dark matter, that mysterious, invisible substance that makes up about 85% of the matter in the universe and whose gravitational pull holds galaxies together. If actions do exist and they make up dark matter, then under the right conditions, they could theoretically clump together to form unimaginably large, diffuse structures called action stars. Don't picture a blazing ball of gas like our Sun. An action star would be more like a gigantic, tenuous cosmic cloud, held together by its own gravity and potentially spanning distances larger than our entire solar system, yet containing the mass of a small moon. These objects would be completely dark and nearly impossible to detect directly, that is, until they encounter a source of an immensely powerful magnetic field. And there are few places in the universe with magnetic fields more intense than the region surrounding a neutron star or a magnetar. Here is where the theory comes to life. Imagine one of these dark, invisible action stars drifting silently through the galaxy. By chance, its path takes it close to a neutron star. The neutron star's monstrous magnetic field, which can be 1,000 trillion times stronger than Earth's, would act like a cosmic shredder on the action star. The field would rip the action star apart, causing it to destabilize and collapse. This collapse wouldn't be a slow process, it would be sudden and catastrophic. In a spectacular conversion of mass into energy, the vast population of actions would rapidly decay or convert into photons, particles of light. But not just any light. The unique physics of this process predicts that the energy would be released predominantly as radio waves. The entire mass energy of the action star, or a significant fraction of it, could be unleashed in an incredibly brief, coherent burst of radio emission. This sudden, enormous release of energy would manifest as a fast radio burst. The entire event would be a one-off catastrophe, completely destroying the action star and leaving behind no trace except for that single, brilliant pulse of radio energy traveling across the cosmos. This theory elegantly explains several puzzling features of one-off FRBS. The immense energy required is provided by the total conversion of an object's mass, and the fact that the action star is destroyed in the process accounts for why we never see a repeat signal from that location. What makes the action star theory so compelling is its profound connection to two of the greatest mysteries in modern science. If this mechanism is indeed responsible for even a small fraction of the fast radio bursts we detect, then we are not just observing stellar physics. We are indirectly observing the behavior and composition of dark matter itself. Each burst could be the death cry of a clump of dark matter, a rare and fleeting moment when this invisible substance is forced to reveal its presence through a spectacular radio flash. It suggests that the answers to the FRB enigma might not lie solely in the violent lives of stars, but in the hidden, dark sector of the universe that permeates all of space. This idea pushes the boundaries of our understanding, suggesting that these brilliant signals could be our first tangible glimpse into the physics of dark matter, offering a potential key to unlocking the secret identity of the universe's dominant form of matter. Moving from dark matter to the very fabric of reality itself, we now turn to a theory that is perhaps the most exotic of all, one that connects these fleeting radio bursts to the violent birth pangs of the universe. This idea doesn't involve stars, black holes, or hypothetical particles, but rather flaws in the fundamental structure of space-time. We are talking about cosmic strings. Imagine the universe in its earliest moments, a seething, unfathomably hot and dense soup of energy and forces. As it expanded and cooled in the first fractions of a second after the Big Bang, it underwent a series of profound phase transitions, much like steam condensing into water or water freezing into ice. Theorists propose that during these transitions, the fabric of spacetime itself might not have cooled evenly. Tiny defects could have been frozen into the very structure of reality as one-dimensional cracks or wrinkles. These are cosmic strings infinitely long but thinner than a single proton, and yet so dense that just a single inch of one could weigh more than Mount Everest. The properties of these hypothetical objects are almost impossible to comprehend. They would be under immense tension, and their gravitational influence would be so powerful that they could act as cosmic lenses, warping the light from galaxies behind them. But it is their potential for violence that makes them a candidate for fast radio bursts. A cosmic string isn't a static scar, it's a dynamic entity. It could form loops that oscillate wildly, or kinks that travel along its length, a T Chinese letter the speed of light. Most dramatically, two cosmic strings could cross, or a single loop could become unstable and snap. In that catastrophic moment of reconnection when two segments of a string violently merge, the theory suggests that an immense amount of pent-up energy, trapped in the string's tension, would be released in an explosive flash. This wouldn't be a chemical explosion or even a nuclear one. It would be a fundamental release of energy from spacetime itself, potentially erupting across the entire electromagnetic spectrum, with a significant portion of that energy manifesting as a coherent, incredibly powerful pulse of radio waves. What makes this explanation so compelling for the most extreme, one-off FRBS is the sheer scale of energy on tap. The theoretical energy released in a cosmic string snap could dwarf even the most powerful supernova, reaching levels that could easily account for the most brilliant fast radio bursts detected from the farthest reaches of the cosmos. Furthermore, this model naturally explains the one-off nature of such a burst. The snapping of a cosmic string loop is a final, singular event. Once it occurs, that particular defect in spacetime is smoothed out, gone forever. There is no engine left to repeat the performance. It is a true cosmic singularity. This provides an elegant explanation for why we see some bursts of such staggering power that they seem to push the limits of what even colliding neutron stars or collapsing magnetars could produce. Connecting fast radio bursts to cosmic strings would be a revolutionary achievement, elevating them from astronomical curiosities to direct probes of fundamental physics. It would mean that we are not just studying the life and death of stars, but we are witnessing the ongoing evolution of spacetime itself, observing the gradual smoothing out of primordial wrinkles left over from the creation of the universe. Each powerful, non-repeating burst could be the death knell of a relic from the first moments of time, a direct echo of the Big Bang reaching out across billions of years. While the evidence for cosmic strings remains entirely theoretical and no direct observation has ever been confirmed, the mere possibility that our largest radio telescopes might be inadvertently recording their final, violent moments is a breathtaking concept. It underscores the profound truth that in our quest to understand these brilliant flashes, we may be touching upon the deepest and most fundamental laws that govern all of existence. Of all the theories we've explored, from colliding stars to snapping cosmic strings, there's one possibility that consistently captures the public imagination more than any other, pushing beyond the boundaries of natural astrophysics and into the realm of the truly profound. This is the alien hypothesis, the tantalizing idea that at least some of these unexplained galactic signals could be evidence of advanced extraterrestrial intelligence. Now, before we let our imaginations run wild, it's crucial to frame this idea with scientific rigor, moving from the speculative to the plausible by considering what astronomers call the search for technosignatures. A technosignature is any measurable sign of technology that could indicate the presence of a civilization beyond Earth. It's a much broader and more sophisticated concept than a simple radio message. It could include things like the atmospheric pollution of an alien world, massive orbiting structures, or indeed powerful, focused beams of energy. The plausibility of this idea hinges on the sheer, focused power of fast radio bursts and a concept known as the Kardashev scale. This scale is a theoretical way to categorize a civilization's level of technological advancement based on its energy consumption. A Type I civilization can harness all the energy available on its home planet. A Type Roman II civilization has advanced to capture and utilize the entire energy output of its star, perhaps by building a theoretical structure like a Dyson sphere. A Type Roman III civilization would control energy on the scale of its entire galaxy. For a Type Roman II or Roman III civilization, the energy required to produce the most powerful fast radio bursts would be trivial, a tiny fraction of their total available power. So, what would such an advanced society use a brief, incredibly powerful radio blast for? One compelling theoretical use is for interstellar propulsion. Imagine a light sail spacecraft, a vast, ultra-thin mirror designed to travel between stars. To propel it, you wouldn't use slow-burning chemical rockets. You would hit it with an intensely powerful, focused beam of energy, a laser or a maser, which is the microwave equivalent. A millisecond blast from such a beam aimed at a distant sail could provide a tremendous kickstart to an interstellar voyage. If that beam were to sweep across our solar system by chance, we would detect it as an incredibly bright, one-off fast radio burst. Another possibility is for communication across unimaginable distances. A tightly focused beam, rather than broadcasting in all directions, is an immensely efficient way to send information across the gulfs between stars. A brief, high-power pulse could punch through the interstellar static, carrying a vast amount of data in a single, compressed package. From the perspective of a super-advanced civilization, these bursts might not be messages at all, but simply the leaked byproduct of their everyday, galaxy-spanning technology, the cosmic equivalent of seeing the brilliant flash from a distant construction site. However, for all its captivating allure, the technosignature hypothesis faces significant scientific counterarguments that cannot be ignored. The first and most obvious is the immense energy required. While a type Roman II civilization might find this energy trivial, the sheer volume of these bursts presents a problem. With instruments like CHIME now detecting thousands of FRBs per year, if even a fraction were artificial, it would imply a galaxy teeming with incredibly advanced civilizations all using this prodigious amount of power simultaneously, which seems statistically unlikely. Furthermore, the signals themselves have characteristics that make them seem inefficient for deliberate communication. They are dispersed across a very broad frequency range. If you were an advanced civilization trying to send a clear, energy-efficient signal, you would likely concentrate your transmission into a very narrow, specific frequency band to maximize the signal-to-noise ratio for the receiver. The fact that FRBs are chirped spread out across a wide spectrum is exactly what we expect from a natural signal that has traveled through a turbulent, ionized plasma, not a carefully engineered beacon. The repeating nature of some bursts also argues against a simple message. The patterns we see are erratic and lack the kind of mathematical structure or predictable redundancy that we would encode in an interstellar message. They feel more like the random hiccups of a stressed natural engine than a purposeful transmission. Ultimately, the alien hypothesis remains, as famed astronomer Carl Sagan would have said, an extraordinary claim that requires extraordinary evidence. While we cannot and should not rule it out completely, the scientific consensus has steadily shifted towards natural astrophysical origins as more and more evidence has mounted for the Magnetar model and others. Yet, the value of considering this possibility is immense. It forces us to think critically about what signs of technology might actually look like and pushes us to refine our search strategies. It expands our perspective on what might be possible in the cosmos. The true answer likely lies in the middle ground. The vast majority of FRBs are almost certainly natural, the spectacular fireworks of a violent and magnetic universe. But in that vast sea of natural phenomena, who is to say that there isn't at least one single anomalous signal, one burst that defies all natural explanation, that could someday turn out to be the first faint hint that we are not alone in the cosmic dark? This lingering possibility is what keeps the search so electrifying, ensuring that with every new flash that lights up our telescopes, we are not just listening to the death of stars, but potentially to the stirrings of intelligence across the void. While we have measured the incredible journeys and immense power of these bursts, there is another, more subtle property of their light that acts as a secret decoder ring, revealing the invisible magnetic forces that have shaped their path. This brings us to the intricate science of polarization, a characteristic of light that transforms a simple flash into a detailed forensic report on its cosmic environment. To understand this, picture a radio wave not just as a wave of energy, but as a wave that oscillates in a specific direction, like a rope you're shaking up and down or side to side. This preferred direction of vibration is what we call polarization. Now, imagine this polarized wave traveling through the vast emptiness of space. If it encounters a region permeated by a magnetic field, something fascinating happens. The magnetic field acts like a cosmic twister, causing the plane of the wave's vibration to slowly rotate as it journeys onward. This effect is named Faraday rotation, after the brilliant scientist Michael Faraday, who first demonstrated how a magnetic field can influence light. The amount of this twisting is not random, it is a precise measurement. It depends directly on the strength of the magnetic field the wave has passed through and the density of the free electrons within that field. Think of it like this: the more twisted the signal appears by the time it reaches our telescopes, the stronger and denser the magnetic environment it must have traveled through. This allows astronomers to perform a kind of cosmic remote sensing. By carefully analyzing the Faraday rotation in a fast radio burst, they can effectively characterize the Faraday screen, the specific region of magnetized plasma that left its fingerprint on the signal. This is how we can peer into environments we can never hope to visit directly. A burst with a small, simple Faraday rotation likely passed through the relatively calm, diffuse magnetic fields of the intergalactic medium. But a burst showing an extreme, complex rotation tells a much more dramatic story, pointing to a source embedded in a local magnetic maelstrom. This is where the puzzle becomes truly compelling. For some repeating fast radio bursts, we have observed that this polarization doesn't just stay constant. It evolves dramatically from one burst to the next, and sometimes even within a single burst. The angle of polarization can swing wildly, and the amount of Faraday rotation can change. This is a game-changing clue. It means the magnetic environment around the source is not static. It is dynamic, turbulent, and changing in real time. A fixed, calm magnetic field would leave a consistent fingerprint on every burst. The fact that the fingerprint is changing tells us we are dealing with a system in violent motion. This observation powerfully supports the model of a young magnetar embedded within the expanding shell of its own supernova remnant. In this scenario, the magnetar is firing its bursts outwards, but each burst has to punch through the supernova remnant's chaotic, swirling magnetic fields. As the remnant expands and evolves, and as the magnetar moves through it, the precise magnetic conditions that each burst encounters on its way out are slightly different. One burst might travel through a relatively clear channel, while the next might pass through a newly formed knot of intensely magnetized plasma, resulting in a completely different Faraday rotation measurement. This dynamic polarization is the direct signature of that cosmic turmoil. Another scenario that could explain such a violently changing magnetic screen places the source of the bursts perilously close to a supermassive black hole. The accretion disk around a black hole, a whirlpool of superheated gas and dust, is a cauldron of incredibly powerful and chaotic magnetic fields. If a magnetar or another source of fast radio bursts were orbiting within this environment, its signals would have to navigate this violent magnetic storm. With each orbit, the geometry would change, and the bursts would sample different, wildly fluctuating magnetic field lines. The observed polarization would swing and shift in a pattern that could, in theory, even reveal the orbital period of the source around the black hole. These detailed polarization measurements are therefore doing much more than just confirming a rough location. They are allowing us to map the intricate magnetic geography around some of the most extreme objects in the universe, turning a brief flash of radio waves into a sophisticated probe of cosmic physics that we could never replicate in any laboratory on Earth. Just when we thought we had the environments for these bursts pinned down, with a clear preference for young, star-forming dwarf galaxies, the cosmos delivered a signal that seemed to break all the established rules. This is the story of FRB 202000120E, a repeater that presented astronomers with a profound and beautiful contradiction. When its location was pinpointed with extreme precision, it wasn't in a chaotic dwarf galaxy or a serene elliptical. It was traced to a stunning and unexpected location, a globular cluster orbiting the nearby spiral galaxy M81, which lies a relatively close 12 million light-years away. Globular clusters are among the most ancient structures in the universe. Picture a dense, spherical swarm of hundreds of thousands, even millions of stars, all gravitationally bound together in a space that is relatively small on a galactic scale. These are cosmic retirement communities composed almost exclusively of elderly, population II stars that are billions upon billions of years old. The intense period of star formation that created these clusters concluded when the universe was in its infancy. There is no gas left, no dust, no material to form new stars. It is the last place in the universe you would expect to find the volatile, youthful engine of a magnetar, which is born from the death of a short-lived massive star. This detection was like finding a roaring, unpredictable wildfire in the middle of a quiet, ancient forest where all the trees died eons ago. This paradox forced a complete rethink of how magnetars, and therefore some fast radio bursts, could come into existence. The traditional path to a magnetar requires a massive star to live its life in a hurry, burning through its fuel in just a few million years before exploding as a supernova. That entire life cycle is impossible in a globular cluster where the last massive star died over 10 billion years in the past. So, if a magnetar is indeed the source of this burst, as the repeating nature strongly suggests, how did it get there? The leading theory proposes a fascinating and slower burning path to stellar violence, one that relies on the unique, crowded conditions of the cluster itself. In such a dense environment, stars are not isolated. They are in constant, close gravitational interaction. Over billions of years, binary star systems can be dynamically formed or altered by close encounters. The most compelling scenario involves two white dwarfs. A white dwarf is the Earth-sized, degenerate core left behind when a Sun-like star reaches the end of its life. It is the final state for the vast majority of stars in a globular cluster. If two white dwarfs are brought together by the cluster's dynamics, they can begin to spiral inward, losing energy to gravitational waves. If their combined mass exceeds a critical limit known as the Chandrasekhar limit, about 1.4 times the mass of our Sun, they can no longer support their own weight. Instead of triggering a standard supernova, this merger can result in a direct collapse, bypassing a supernova explosion and forming a neutron star in what is known as an accretion-induced collapse. If this newly born neutron star is spun up during the merger process and possesses a sufficiently strong magnetic field, it could be born directly as a magnetar, billions of years after every other star in its neighborhood settled into a quiet old age. Another, even more exotic possibility involves a different kind of binary pair, a white dwarf and a neutron star that already exists from the cluster's very early history. In this scenario, the white dwarf slowly transfers its mass onto the neutron star over eons. As the neutron star gains mass, it can be spun up to incredible speeds, and the influx of fresh material could somehow rejuvenate its magnetic field, effectively turning an old, quiet neutron star into a newly activated, repeating magnetar engine. This process is like throwing a bucket of gasoline onto fading embers, causing them to flare back to life with a new and violent intensity. Both of these theories share a common, revolutionary thread. They demonstrate that magnetars do not necessarily have to be young. They can be formed or reactivated long after the era of star formation has ended, through the slow, patient choreography of stellar dynamics in dense environments. The existence of FRB 202000120e is therefore more than just another data point. It is direct evidence that the universe has multiple, hidden pathways for creating these magnetic monsters, challenging our textbook understanding of stellar evolution and proving that even the oldest, quietest corners of the cosmos can still harbor engines of incredible power and mystery. As we explore the intricate lives of these repeating cosmic beacons, scientists have developed a particularly vivid and compelling model to explain their erratic behavior, a theory that has earned the dramatic nickname of the dragon. This isn't a model of a serene, isolated object, but rather a portrait of a system in violent, ongoing turmoil, a celestial beast that breathes fire in unpredictable bursts. The dragon model attempts to answer one of the most persistent questions about repeaters. If their engine is a magnetar, what provides the recurring fuel for its outbursts, and why do they come in such a chaotic, staccato rhythm instead of a steady, predictable pulse? The answer, this model suggests, lies not just within the magnetar itself, but in a tortured relationship with its own shattered remains. The story of the dragon begins with a cataclysm in the magnetar's past. Imagine this neutron star suffering a truly colossal starquake, an event so violent it's classified as a giant flare. This isn't a small crack in the crust, it's a world-shattering event. The immense magnetic energy stored in the star is released in a torrent, violently ejecting a significant amount of material from the magnetar's own solid surface out into the surrounding space. This ejected material, composed of the star's own shattered crust, doesn't necessarily just fly off into the void. Instead, if the conditions are right, it can become trapped by the magnetar's overwhelming gravity, settling into a swirling, chaotic orbit around the central star. This forms a debris disk, a torus of super-dense metallic rubble circling the Dragon's lair. This disk is not like the pristine, planet-forming disks around young stars. It is a hellish ring of wreckage, a constant reminder of the magnetar's past fury and a reservoir of potential future violence. This is where the Dragon's breath is fueled. The magnetar and its debris disk exist in a precarious gravitational balancing act. The disk is not perfectly stable. Clumps of material within it can collide, merge, and gradually lose orbital energy. Over time, some of this rocky, metallic debris begins to spiral inward, pulled by the magnetar's immense gravity. Now, picture a mountain-sized chunk of this incredibly dense material, a fragment of neutron star crust finally losing its fight against gravity and plunging down toward the star's surface. The impact is not a gentle landing. When this massive projectile strikes the magnetar's solid, ultra-rigid crust, it doesn't just create a splash, it delivers a colossal, localized hammer blow. The impact transfers a huge amount of kinetic energy directly into the crust, triggering a powerful, focused starquake. This is not a quake caused by internal magnetic stresses alone, but one initiated by a direct physical assault from above. The resulting energy release is the fast radio burst we detect. The impact and the subsequent starquake create a violent disturbance in the magnetar's magnetosphere, the region dominated by its unimaginably strong magnetic field. This disturbance launches a shock wave through this magnetized plasma, accelerating particles and generating an intensely coherent blast of radio waves that rockets out into space. The irregularity of the bursts is perfectly explained by this chaotic accretion process. The inflow of material from the debris disk is not a steady stream. It is lumpy, unpredictable, and episodic. Sometimes only small pebbles fall, producing weaker bursts. Other times, after a long period of build-up, a truly massive chunk of crust plummets down, resulting in an extraordinarily bright and energetic radio blast. The Dragon doesn't breathe fire on a schedule. It roars when it is fed, and its feeding times are as random as the collisions within its orbiting debris ring. This model elegantly accounts for the wide variation in energy and timing observed among repeating FRB sources. A magnetar with a large, massive debris disk might be a very active dragon, producing frequent bursts of varying strength as it steadily consumes its surrounding wreckage. Another, with a smaller or more stable disk, might only produce the occasional brilliant roar when a rare, large fragment manages to spiral inward. The Dragon model beautifully ties together the idea of a persistent engine, the magnetar, with an external, stochastic fuel source, the debris disk, creating a system capable of the long-lived, erratic, and immensely powerful radio outbursts that continue to challenge and fascinate astronomers. It paints a picture of a cosmic aftermath, where a star's own self-destruction creates the very conditions for its continued, violent outbursts, a cycle of creation and destruction happening on a scale almost too grand to comprehend. While we've been charting the immense power and cosmic journeys of these bursts, there's an entire frontier of the radio spectrum that has proven incredibly challenging to explore, the realm of low frequencies. Most fast radio bursts have been discovered in the higher frequency radio bands, typically around 1 to 2 GHz, a range where our telescopes are highly sensitive and the signals cut clearly through the cosmic static. But what happens when we try to listen to these cosmic flashes at much lower pitches, down in the hundreds of megahertz range? The answer reveals as much about the environments these signals travel through as the sources that create them. Imagine the difference between a high, clear whistle and a low, booming drum. The whistle can travel far in open air, while the boom is more easily muffled by obstacles or absorbed by the environment. Similarly, low-frequency radio waves are far more susceptible to being scattered, absorbed, or scattered by the charged particles they encounter. For a long time, many astronomers assumed that detecting an FRB at very low frequencies would be nearly impossible, that these signals would simply be lost in the fog of the interstellar and intergalactic medium. This is why the first confirmed detections of low-frequency counterparts were so significant. They weren't just finding the same signal at a different pitch. They were proving that the signals could survive a much more arduous journey, and in doing so, they provided a powerful new diagnostic tool. The key phenomenon at play here is something called scattering. As a radio burst travels through clouds of turbulent plasma, whether in the interstellar medium of its own galaxy, the intergalactic void, or the turbulent environment right near the source, the different paths the waves take can cause the signal to spread out or scatter in time. This scattering effect is dramatically stronger at lower frequencies. A burst that appears as a sharp millisecond spike at 1.4 GHz might be noticeably smeared out over several milliseconds at 800 MHz and could be stretched into a much longer, blurred echo at even lower frequencies. By carefully measuring this scattering, astronomers can effectively measure the turbulence of the material the signal has passed through. A heavily scattered low-frequency signal acts like a cosmic probe, telling us that the burst had to fight its way through an exceptionally rough and dense plasma, perhaps the supernova remnant surrounding a young magnetar or the dense heart of its host galaxy. One of the major players in this low-frequency hunt has been the Low-Frequency Array, or LOFR, a vast network of thousands of small antennas spread across Europe. While LOFR's primary focus isn't hunting for FRBs, its incredible sensitivity to low-frequency radio waves down to around 30 MHz makes it a perfect instrument for follow-up observations. The strategy often involves a powerful synergy between telescopes. A wide-field survey instrument like CHIME or the Australian Square Kilometre Array Pathfinder will first detect a bright burst at higher frequencies and instantly send out an alert. Within seconds, telescopes like LOFR can slew to the same coordinates and stare, hoping to catch the afterglow or any subsequent bursts from the same source at their much lower frequencies. This coordinated effort has paid off, leading to the detection of low-frequency bursts from several known repeating sources. These observations have revealed that some repeaters are remarkably robust, producing bursts that are detectable across an astonishingly wide range of the radio spectrum, from as high as several gigahertz down to a few hundred megahertz. However, these successes have also unveiled a new puzzle. For many other sources, the signal seems to abruptly die out or drop off below a certain frequency threshold. We might see a repeater firing off bright bursts at 1.4 GHz, but see absolutely nothing from it at 400 MHz. This isn't because the telescope isn't looking, it's a real physical effect. This frequency cutoff is another crucial piece of environmental evidence. It suggests that the source is embedded in an extremely dense screen of ionized material. The low-frequency radio waves, being more susceptible to absorption, simply cannot escape this local fog. Each repeater, therefore, has its own unique low-frequency limit, a signature of the density and turbulence of its immediate surroundings. By cataloging these cutoff frequencies across different sources, astronomers can begin to classify the types of environments that host these enigmatic engines, distinguishing between, for example, a magnetar floating in a relatively clear region of space and one that is deeply enveloped in the dense, turbulent shell of its recent supernova. Pushing to even lower frequencies presents even greater challenges, but the potential rewards are immense. The lowest frequencies of the radio spectrum, below about 100 MHz, are notoriously difficult to observe from Earth's surface because they are flooded with interference from human activity and reflected by our planet's ionosphere. Yet, venturing into this domain could unlock secrets about the most extreme magnetic fields in the universe. There is a theoretical expectation, rooted in the physics of neutron star magnetospheres, that the coherent radio emission we see as an FRB should have a low-frequency cutoff that is directly tied to the strength of the magnetic field at its source. Detecting a burst at, say, 50 MHz would immediately place an upper limit on the magnetic field strength of the object that created it, providing a direct measurement that is otherwise incredibly difficult to obtain. While such a detection remains elusive, it represents a thrilling frontier. The ongoing hunt for these low-frequency whispers is more than just an exercise in technical prowess. It is a fundamental part of building a complete picture of these cosmic explosions, allowing us to listen to the universe's loudest shouts across their full sonic range, and in the process to understand the invisible barriers they must overcome to reach our telescopes. But what if the secret to the immense brightness of some of these bursts isn't just about the power of the source itself, but is instead shaped by the cosmic landscape it travels through? This brings us to a fascinating theory that transforms the vast, empty voids between galaxies from a passive backdrop into an active, dynamic lens. Imagine you're trying to see a distant lighthouse on a foggy night. Sometimes the fog is perfectly uniform and the light appears as a steady, constant glow. But other times the fog has pockets of differing density, and the light seems to flicker and dance, occasionally flashing with a surprising, momentary intensity. This is the essence of scintillation, a phenomenon that could be playing out on an intergalactic scale with fast radio bursts. The space between galaxies is not a perfect vacuum. It's filled with a tenuous, ionized plasma, a soup of free electrons. This intergalactic medium isn't smooth. It has ripples, clouds, and variations in density, a kind of cosmic texture created by galactic winds, ancient supernova explosions, and the gravitational pull of dark matter filaments. When a radio signal from a distant FRB passes through this patchy fog, something remarkable can happen. The ripples in the plasma can act like a series of natural lenses, bending the radio waves. If the alignment is just right, these lenses can focus the signal, channeling its energy and making it appear hundreds of times brighter to our telescopes than it would otherwise be. It's as if the universe itself is providing a temporary magnifying glass, turning a bright flash into a truly colossal one. This theory of interstellar and intergalactic scintillation provides an elegant explanation for one of the most puzzling aspects of FRB observations: the wild variation in signal strength even from the same repeating source. We might detect a series of bursts from a single magnetar, with most being relatively modest in power, and then suddenly, one burst arrives that is dramatically more luminous. It's tempting to assume that this particular burst was an intrinsically more powerful explosion from the source, but the lensing theory offers an alternative. The source might be putting out a fairly consistent level of power, but the path its signal takes through the intergalactic medium is constantly changing. As the source galaxy, the lensing clouds of plasma, and our own Milky Way all move relative to one another, the alignment of this natural lens evolves. The burst that appears exceptionally bright might not be an unusually violent event. It might simply be one whose light happened to pass through a perfect, fortuitous knot of dense plasma that focused its energy directly toward Earth. This would mean that the recorded brightness of a burst is not a pure measure of its intrinsic power, but a combination of that power and the lensing amplification it experienced along its journey. For the most luminous bursts ever detected, this raises a profound possibility. Could their record-breaking intensity be due to an almost perfect lensing alignment, amplifying a signal that was already powerful into something that defies our expectations? It effectively decouples the observed brightness from the engine's output, suggesting that some of the most extreme events in our catalogues might be cosmic mirages, magnified by the intricate structure of the space between galaxies. This idea doesn't just explain brightness variations, it also helps us understand the structure of the intergalactic medium itself. The specific patterns of this scintillation, how quickly the signal flickers and over what frequency range it occurs, act as a fingerprint of the turbulent plasma it has traversed. A signal that shows rapid scintillation suggests it has passed through a region of fine, turbulent structure with many small lensing clouds. A signal with slower, broader scintillation hints at larger, more coherent structures in the plasma. By analyzing these patterns across many different FRBs coming from different distances and directions, astronomers can effectively perform a tomography of the cosmos. They can map the texture and turbulence of the invisible material that weaves the cosmic web together. This turns every detected burst into not just a message from its source, but a probe of the vast, interconnected highways of plasma that define the large-scale structure of our universe. The very phenomenon that complicates our understanding of the burst's power becomes a powerful new tool for studying the distribution of the universe's normal matter, much of which has been notoriously difficult to locate and quantify. The intergalactic medium is no longer just empty space to be traversed. It is an active participant in the story, a colossal lens that can magnify, distort, and ultimately reveal its own hidden structure through the brilliant flashes that pass through it. This journey through unexplained signals reveals a profound truth. Sometimes the greatest value of a mystery is not the solution itself, but the new questions it allows us to ask. As we catalogued these brilliant flashes, we began to notice something intriguing about the journey of their light. Each burst carried a hidden record of its voyage through the cosmos, a clue that these signals were more than just cosmic explosions. They were potential keys to solving one of cosmology's most persistent and frustrating puzzles. For decades, scientists have known that a huge portion of the universe's normal matter, the kind that makes up you, me, planets and stars, has simply been missing. We call this the missing baryon problem. When we add up all the matter we can directly see in stars, galaxies, and the cool gas around them, it accounts for less than half of the ordinary matter that our most robust theories of the Big Bang insist must exist. Where in the universe could this vast reservoir of atoms be hiding? The answer, it turns out, might be written in the very fabric of the signals we've been studying. Remember the concept of dispersion measure, the telltale smearing of a fast radio burst signal where the high-frequency waves arrive slightly before the low-frequency waves. This smearing isn't a flaw, it's a precise measurement. It acts as a cosmic odometer, counting the total number of free electrons the radio waves have encountered on their epic journey from their source to our telescopes. Every electron along the path contributes to this delay. For a signal traveling billions of light years, the vast majority of this delay isn't caused by the material inside its host galaxy or even our own Milky Way, but by the incredibly sparse ionized gas that fills the unimaginably vast spaces between galaxies. This material, known as the warm-hot intergalactic medium, or WHIM for short, is the prime suspect for the missing baryons, theorized to exist as a faint, superheated fog threaded along the invisible filaments of the cosmic web. The WHIM is extraordinarily difficult to detect directly. It's too hot to show up in optical telescopes and too diffuse to emit strong X-rays, making it virtually invisible to most traditional observation methods. But it is precisely this kind of tenuous, ionized plasma that leaves a clear and measurable fingerprint on a traveling fast radio burst. This is where the true power of these signals as cosmic tools becomes astonishingly clear. Each localized fast radio burst with a known distance gives astronomers a single, clean measurement. They can take the total dispersion measure, the total electron count from the burst's journey, and subtract the known contributions from our own galaxy and the burst's host galaxy. What remains is the amount of material the signal passed through in the intergalactic medium. By doing this with just one burst, you get a single data point, a measurement of the average density of the cosmic web along one specific narrow sightline. But with the flood of new detections from instruments like CHIME, we are no longer limited to a single measurement. We now have hundreds and soon thousands of these precise probes, each one sampling a different path through the universe, each one piercing the cosmic fog along a unique trajectory. By combining this growing catalog of dispersion measures, astronomers are beginning to do something revolutionary. They are constructing a three-dimensional map of the universe's missing matter. Think of it like this. Imagine you're in a profoundly dark, foggy forest at night, and you have no map. You can't see the trees or the paths. But then, thousands of distant friends all flash their camera flashes at you from different known distances and directions. By carefully measuring how much each flash is dimmed and diffused by the fog it traveled through, you can begin to reconstruct the density and structure of the fog itself. You can map the clearings and the thick patches. That is exactly what we are now doing on a cosmic scale. Fast radio bursts are those brilliant, momentary flashes. Their dispersion measures tell us the thickness of the cosmic fog they penetrated. By analyzing them collectively, we are tracing the outline of the cosmic web, finding the denser filaments of the WHIM where the missing baryons have been hiding all along. This transforms the mystery of these signals from a question of stellar origins into a fundamental tool for cosmology. They are no longer just flashes in the dark. They are the flashlights we are using to illuminate the invisible architecture of the entire universe, finally accounting for the atoms that have been lost in the vast, dark spaces between the stars. Now, as we consider the most extreme environments in the cosmos, we must turn our attention from the stellar scale to the galactic, to the titanic engines that reside at the very heart of galaxies. This brings us to a theory for one-off bursts that is as grandiose as it is plausible. The idea that some of these singular flashes are not the death cries of stars, but the colossal hiccups of supermassive black holes. At the center of nearly every large galaxy, including our own Milky Way, sits one of these gravitational monsters with a mass millions or even billions of times that of our Sun. But a quiet, isolated black hole is not the source of the drama. The action happens when these behemoths are actively feeding, pulling in vast quantities of gas and dust from their surroundings. As this material spirals inward, it forms a superheated, swirling structure known as an accretion disk, and from the poles of this system, they can launch jets of plasma traveling at nearly the speed of light. These are not gentle streams. They are the most powerful and focused particle accelerators in the universe, stretching for thousands of light years into intergalactic space. Within these relativistic jets, theorists propose, could lie the secret to some of the most powerful one-off fast radio bursts ever detected. To understand how a jet could produce such a brief, brilliant flash, we need to look at the chaotic physics occurring within it. These jets are not smooth, laminar flows. They are highly turbulent, filled with knots and shocks as different parts of the stream travel at slightly different velocities. Imagine two high-speed trains racing down parallel tracks, one suddenly rear-ending the other. This is the concept of an internal shock. When a faster-moving clump of plasma within the jet slams into a slower-moving clump ahead of it, the resulting collision is ferociously energetic. The sudden deceleration converts a tremendous amount of kinetic energy into radiation, potentially creating a brief, intense flare across the electromagnetic spectrum. If the conditions are just right with the right density of particles and the presence of a strong, ordered magnetic field, this shock could also generate a highly coherent burst of radio waves, a shock front that acts like a natural maser, amplifying radio emission into the signature spike of a fast radio burst. Another mechanism operating within these jets is equally capable of unleashing a torrent of energy: magnetic reconnection. The jets are permeated by fantastically powerful and complex magnetic fields, lines of force that are twisted and wound up by the rotation of the accretion disk and the black hole itself. These field lines can become strained to a breaking point, and when they snap and reconfigure into a lower energy state, a process called magnetic reconnection, they release their pent-up energy with explosive force. This is the same fundamental process that powers solar flares on our sun, but scaled up to a truly mind-boggling magnitude. In the environment of a supermassive black hole jet, a single reconnection event could instantaneously accelerate electrons to near light speed, causing them to spiral wildly along the newly formed magnetic field lines and emit a brilliant, short-duration pulse of synchrotron radiation concentrated in the radio band. The entire event, from the snapping of the field lines to the release of the radio wave, could be over in milliseconds, appearing to us as a one-off fast radio burst of incredible power. This theory elegantly explains several key characteristics of one-off bursts. First, it accounts for the sheer energy required for the most luminous events. The gravitational potential energy available from a feeding supermassive black hole is virtually limitless on human scales, easily capable of powering bursts that can be seen across the universe. Second, it naturally produces one-off events. While the jet itself is persistent, the specific internal shock or magnetic reconnection event that creates a particular burst is a localized, ephemeral catastrophe within that larger flow. It's a single thunderclap in a perpetual storm. The storm rages on, but that specific clap of thunder never repeats in exactly the same way. Finally, this model provides a natural home for these bursts in a variety of galaxy types. Active galactic nuclei, the sites of these feeding black holes, exist in both spiral and elliptical galaxies, which could explain why we have detected one-off bursts originating from such a diverse range of galactic environments. The supermassive black hole jet theory thus positions these enigmatic signals not as the end of a star, but as a byproduct of the MOST Chinese letter and powerful engines the universe has to offer, a brief flash of light from the heart of a cosmic maelstrom. As we push the observational frontiers of fast radio bursts to their absolute limits, we encounter signals that do more than just traverse vast distances. They function as cosmic time machines, carrying encoded information from the universe's infancy. The most distant FRBs, those exhibiting the very highest dispersion measures, are not merely statistical outliers. They are potential messengers from the epoch of reionization, a pivotal and poorly understood era that occurred when the universe was only a few 100 million to 1 billion years old. This period marked the end of the cosmic dark ages, a time when the first stars, galaxies, and quasars ignited, flooding the cosmos with ultraviolet radiation that systematically stripped electrons from the neutral hydrogen atoms that filled intergalactic space. Detecting a signal that has journeyed from this specific epoch would be the astronomical equivalent of unearthing a pristine fossil from the dawn of complex life on Earth, offering a direct probe of conditions during one of the most transformative chapters in cosmic history. The unique value of these ancient bursts lies in the specific information encoded in their dispersion. For a signal originating from the epoch of reionization, a significant portion of its total dispersion measure would be imprinted by the very process of reionization itself. As the burst travels through the early universe, it encounters a medium that is not uniformly ionized. It must pass through pockets of lingering neutral hydrogen, then through regions that have already been ionized by the first brilliant sources of light, and finally through the advancing fronts of ionization surrounding the earliest galaxies. This complex, patchy journey leaves a distinct fingerprint on the signal's propagation. By meticulously analyzing the detailed structure of the dispersion in an FRB from this era, how the smearing of the signal changes across different, very low radio frequencies, cosmologists could, in theory, map the geometry and progression of reionization. They could determine whether it was a slow, gradual process driven by many small early galaxies, or a more rapid, dramatic event catalyzed by a smaller number of immensely bright quasars. Each ultra-distant FRB would provide a single, one-dimensional core sample through this cosmic transformation, and a collection of such bursts from different directions would allow us to reconstruct a three-dimensional view of how the universe lit up, turning an opaque fog into the transparent void we see today. Beyond charting the ionization state of the universe, these primordial signals could also shed light on the nature of the very first generation of stars, known as population 3 stars. These stellar titans are thought to have been hundreds of times more massive than our Sun, composed purely of hydrogen and helium, and living ferociously short lives that ended in spectacular pair instability supernova that completely obliterated the star, leaving no remnant behind. The environment surrounding such an object would have been unlike anything in the modern universe: pristine, violent, and incredibly turbulent. If a fast radio burst were to be generated in such a setting, perhaps by the collapse of one of these behemoths or the magnetic fury of a hypothetical first-generation magnetar, the signal's properties would be fundamentally shaped by that unique environment. The local dispersion and scattering around the source would tell us about the density and metal content of the gas in these primordial galaxies. The absence of heavy elements would mean the surrounding plasma behaved differently, potentially allowing the radio emission to propagate in ways that are no longer possible in today's metal-enriched cosmos. Detecting a burst from this era would thus be a double discovery. It would confirm the existence of the burst's engine, but it would also provide our first ever observational data point on the physical conditions within the universe's first stellar nurseries, places we have only been able to model with supercomputers until now. This transforms the pursuit of high-dispersion FRBs from a cataloging exercise into a form of cosmic archaeology. Just as archaeologists use pottery shards and stone tools to infer the structure of ancient civilizations, cosmologists could use these dispersed radio signals to infer the properties of the first structures to emerge after the Big Bang. The discovery of even a handful of bursts confirmed to originate from the epoch of reionization would provide invaluable, otherwise unattainable constraints on our models of early structure formation. They could help answer fundamental questions: how quickly did the first galaxies assemble? How efficient were they at producing ionizing photons? What was the typical mass of the first stars? By using FRBs as backlights to illuminate the infant cosmos, we gain a direct observational tool to study an era that is currently only accessible through the faint, redshifted glow of the cosmic microwave background or the incredibly challenging observations of the most distant quasars and galaxies. These signals represent a new and powerful probe, one that carries within its brief flash the potential to rewrite our understanding of the universe's first billion years and illuminate the very origins of the cosmic dawn. As our catalog of unexplained signals grew and our instruments became more sensitive, the scientific community grew increasingly confident in its ability to distinguish a true cosmic event from mere earthly noise. But then came a signal that served as a powerful and humbling reminder that the greatest challenges in this field are sometimes not in the stars but right here at home. This is the story of the so-called Christmas burst, a mysterious event that for a brief, exciting period looked like it could be the most important discovery of the year, only to unravel in a way that exposed the delicate interplay between cutting-edge science and the hidden complexities of our own world. It was December 25, 2010, and the Parkes Radio Telescope in Australia was, as usual, silently scanning the heavens. In the midst of the holiday quiet, its computers registered a strong, dispersed burst that matched the profile of a genuine fast radio burst. The timing, combined with the signal's apparent characteristics, created a surge of excitement. Had they just received a cosmic Christmas gift? The initial data was promising, and for a time it was treated as a serious candidate, another piece in the growing puzzle of FRBs. However, doubt soon began to creep in. The signal had a peculiar quality that experienced radio astronomers found just a little bit too perfect, a little too clean. Furthermore, it seemed to be an isolated event. No other telescope had detected it, despite the fact that its apparent strength should have made it visible across a wide area. The investigation that followed was a masterclass in scientific skepticism and forensic astronomy. Researchers began to methodically trace back the signal's path, not through the cosmos, but through their own data logs and the local geography. They analyzed the signal's polarization, its frequency structure, and its timing with an excruciating level of detail, looking for any tiny anomaly that would betray a terrestrial origin. The key breakthrough came when they noticed that the signal's properties perfectly matched what would be expected from a powerful, ground-based radar transmission. But who would be operating such a powerful radar in the remote Australian outback, and why would it produce a single, burst-like signal that so cleverly mimicked a cosmic event? The answer, when it finally emerged, was as shocking as it was absurd. Through careful detective work and collaboration with government agencies, the astronomers discovered that the signal was not a message from the stars, but the result of a secret, unauthorized test by a military organization. A nearby defense facility had been running a covert radar experiment, and through a combination of atmospheric conditions and a fortunate or unfortunate alignment with the telescope's beam, the radar's signal had bounced off aircraft or other objects in the sky and been reflected directly into the park's dish. The reflection created the exact same dispersive smearing that a signal traveling through intergalactic space would produce, making it a nearly perfect counterfeit. The Christmas burst was not a celestial phenomenon. It was a phantom, a ghost created by human technology and the tricks of Earth's own atmosphere. The unauthorized nature of the test added a layer of real-world drama and frustration, highlighting the fact that radio astronomers are not just competing with the natural background noise of the universe, but also with the ever-expanding electronic footprint of our own civilization. This episode, while deeply disappointing at the time, served an invaluable purpose. It underscored the pervasive and insidious challenge of radio frequency interference, or RFI. Our modern world is saturated with radio transmissions, from Wi-Fi and cell phones to satellites, aviation radar, and even the humble microwave oven, as the earlier Puritan story proved. All of this electronic chatter creates a constant, low-level static against which astronomers must try to hear the faint whispers of the cosmos. The Christmas burst was a particularly sophisticated example, but RFI is a daily battle. It forces observatories to be built in the most remote radio-quiet zones on the planet, and it requires the development of increasingly sophisticated digital filters and signal processing algorithms designed to recognize and reject the distinctive signatures of human-made transmissions. Ultimately, the legacy of the Christmas burst is one of refined rigor. It directly led to the implementation of even more stringent verification protocols that are now standard practice across the globe. The gold standard today is multi-telescope verification. When a potential FRB is detected by one instrument, like CHIME in Canada or a SKAP in Australia, an automatic alert is sent out instantly to a network of other observatories worldwide. If the signal is truly cosmic, these other dishes, pointed at the same patch of sky from different continents, should also be able to detect it. This powerful form of independent confirmation is the ultimate defense against phantom signals, whether they come from a secret military test, a passing satellite, or a faulty piece of equipment in an observatory kitchen. The Christmas burst was a failure that made the entire field stronger, a cautionary tale that reminds every scientist that in the hunt for universal truths, they must first be absolutely certain the signal they are chasing isn't just an echo from their own backyard. This journey through the cosmos has revealed engines of immense scale, from magnetars to colliding neutron stars. But what if some signals originate from objects that are almost impossibly small, yet whose existence would rewrite the first chapter of the universe itself. This brings us to a theory that connects the quantum realm to the cosmic, suggesting that some of the faintest, most fleeting signals in the sky could be the death spasms of black holes born in the Big Bang. The concept hinges on the existence of primordial black holes. Unlike the stellar mass black holes formed from collapsing stars or the supermassive giants at galactic centers, primordial black holes are hypothetical objects that could have been forged in the extreme density fluctuations of the universe's very first second. They could span a vast range of masses, from smaller than an atom to many times the mass of our Sun. And according to a revolutionary idea from Stephen Hawking, the very smallest of these ancient relics should be dying right now. The mechanism behind this death is known as Hawking radiation. Classical physics tells us that nothing can escape a black hole's event horizon, but quantum mechanics paints a more nuanced picture. At the subatomic level, space is not empty. It is a seething quantum foam where pairs of particles and antiparticles constantly blink in and out of existence. Normally, these virtual pairs annihilate each other almost instantly. However, Hawking realized that if such a pair pops into being right at the edge of a black hole's event horizon, a bizarre thing can happen. One particle might fall in while its partner escapes into space. From the perspective of a distant observer, the black hole has just emitted a particle. This process slowly siphons mass and energy away from the black hole, causing it to evaporate. For a massive black hole, this evaporation is immeasurably slow, a trickle over timescales longer than the current age of the universe. But for a very small, low-mass primordial black hole, the story is different. The smaller the black hole, the more intense its Hawking radiation and the faster it evaporates. A primordial black hole with a mass of around 1 billion metric tons, roughly the mass of a large mountain squeezed into a size smaller than a proton, would have a lifetime roughly equal to the current age of the universe, 13.8 billion years. This means a whole population of these tiny black holes created in the cosmic dawn would be reaching the end of their lives at this very moment, and what an end it would be. The evaporation process is not a gentle fade to black. As the black hole loses mass, its temperature increases and the rate of radiation accelerates in a runaway feedback loop. In the final tenth of a second of its life, the black hole's temperature would skyrocket and it would emit a tremendous burst of high-energy particles and radiation. The final instant would be a catastrophic total conversion of its remaining mass into energy, a spectacular final pop that would, for a fleeting microsecond, outshine entire stars. The energy released in this last explosive moment would be concentrated in gamma rays, but a significant portion of that energy could also manifest as a coherent burst of low-frequency radio waves. This would not be the brilliant millisecond flash of a typical fast radio burst from a distant galaxy. The signal from an evaporating primordial black hole would be vastly weaker and unimaginably shorter, lasting perhaps only nanoseconds or picoseconds. Its frequency would also be much higher, likely in the gigahertz or even terahertz range, more akin to a cosmic click than a sustained shout. This fundamental difference in duration and energy is why this theory is not proposed as an explanation for the powerful FRBS we have catalogued. Instead, it suggests an entirely new, hidden population of ultra-fast radio transients, a faint, high-pitched static of dying quantum black holes that has so far eluded our detection. The hunt for these whispers is one of the most challenging frontiers in observational astronomy. Our current radio telescopes are simply not designed to catch events that are this brief. They are optimized for millisecond duration pulses, not for signals that are over 1 million times shorter. Detecting a nanosecond burst would require a completely different kind of instrument, one with incredibly fast electronics and a colossal bandwidth to capture the entire event in a single hyper-fast snapshot. Furthermore, because primordial black holes would not be confined to galaxies, they could be drifting anywhere in the dark halos around galaxies or even in the emptiness of intergalactic space. Their signals would arrive from random, unpredictable directions with no visible counterpart. The confirmation of just one such signal would be a scientific triumph of unparalleled proportions. It would achieve two extraordinary things at once. First, it would provide the first direct empirical evidence for the existence of Hawking radiation, confirming a cornerstone of theoretical physics that has stood for 50 years but has never been directly observed. Second, and perhaps even more profound, it would prove the existence of primordial black holes. Finding them would be a direct window into the conditions of the Big Bang, offering tangible evidence for the wild density variations that must have existed in the universe's first moments. It would also offer a compelling solution to the long-standing dark matter mystery, as these ancient black holes could constitute at least a portion of the invisible mass that holds galaxies together. So, while our telescopes listen for the mighty roars of magnetars and the crashes of neutron stars, a silent hunt continues in the background for the faint, final pops of the universe's smallest and oldest black holes, each one a potential key to unlocking the quantum secrets of creation itself. The real power to solve a cosmic mystery often lies not in listening to just one voice, but in hearing a full choir sing in unison. This is the core idea behind the most exciting modern approach to fast radio bursts, a field known as multi-messenger astronomy. For too long, we've been like detectives examining a crime scene with only one piece of evidence, a single blurry photograph. We've had the brilliant radio flash, a compelling story in itself, but to truly understand the crime, we need the fingerprint dust, the security camera footage, and the forensic report. Multi-messenger astronomy is our way of gathering that full suite of evidence, looking for the same cosmic event across the entire spectrum of physics, not just in radio waves, but in gamma rays, X-rays, optical light, and even by detecting the ghostly passage of neutrinos or the ripples in spacetime itself known as gravitational waves. A single confirmed detection of a counterpart signal in any of these other messengers would be the ultimate key, instantly narrowing down the list of suspects and providing a definitive answer to the central question: what is the engine behind these bursts? The challenge, of course, is the breathtaking speed of these events. A fast radio burst is over in less time than it takes for a camera's shutter to click. To catch its counterparts, we need a global network of observatories that can react not just quickly, but instantly. This has led to the creation of a sophisticated, automated alert system that turns the entire planet into a single, coordinated instrument. When a radio telescope like CHIME or a SKAP detects a bright burst, its computers don't just log the data and move on. Within seconds, they automatically distribute a digital alert packet across the globe. This packet contains the most crucial information: the exact coordinates in the sky the burst came from, the time it was detected, and its estimated distance. This alert acts as a cosmic starting pistol. The moment it is received, observatories on the ground and in space begin to swing into action. Robotic optical telescopes in Chile, the Canary Islands, and Hawaii automatically interrupt their pre-programmed schedules, slewing their massive mirrors to stare at the spot of the burst, searching for a fleeting flash of visible light or a fading afterglow. In orbit, space-based observatories like the Neil Gehrels Swift Observatory or the Fermi Gamma Ray Space Telescope reorient their sensitive instruments, scanning the same patch of sky for any high-energy signature that coincided with the radio blast. The holy grail of this entire effort would be to catch a fast radio burst in the act of producing gravitational waves. Imagine the scene: a radio telescope registers a brilliant millisecond flash. At almost the exact same moment, thousands of kilometers away, the incredibly sensitive lasers of the LIGO or Virgo gravitational wave observatories detect a subtle, telltale wobble in the fabric of spacetime. That combination would be utterly transformative. If the gravitational wave signal had the characteristic chirp of two neutron stars spiraling together and merging, it would provide irrefutable proof that at least some one-off FRBs are indeed produced by these catastrophic collisions. The gravitational wave signal would tell us the masses of the objects involved and the precise dynamics of their final moments, information that is simply impossible to extract from the radio burst alone. Similarly, a coincident flash of high-energy gamma rays would be a massive clue. Gamma-ray bursts are already known to be the signatures of the most violent explosions in the universe, the births of black holes and the mergers of compact objects. Finding a gamma-ray burst that perfectly aligns in time and direction with a fast radio burst would strongly tether the FRB to a specific cataclysmic stellar death. We have already had tantalizing hints that this multi-messenger approach is on the right track. The detection of a fast radio burst from the galactic magnetar SGR 1935+2154 was, in itself, a form of multi-messenger discovery, as it was accompanied by a storm of X-ray activity from the same object. This single event powerfully linked magnetars to the FRB phenomenon, but for the more distant extragalactic bursts, the associations have been more elusive. There have been a few reported instances of a potential, very faint X-ray or optical counterpart, but these detections are often at the very limit of our instruments' capabilities and are difficult to confirm. The reason for this elusiveness might be a fundamental property of the bursts themselves. The radio emission we see is likely highly beamed, focused into a narrow jet like the beam from a lighthouse. If that jet is pointed directly at Earth, we see the brilliant radio flash, but the lower energy counterpart emission, the X-rays or the visible light from the expanding fireball or the surrounding heated material, might be emitted in a much broader spray, like the general glow around a lighthouse. From billions of light-years away, this surrounding glow would be incredibly faint, requiring the most powerful telescopes to have any hope of seeing it, and only if they look within minutes or hours of the initial burst. This is why the speed of the automated alert system is so critical. The afterglow of a fast radio burst might fade to black in the time it takes you to watch a movie. The pursuit doesn't end with light and gravitational waves. Scientists are also searching for an even more exotic counterpart, neutrinos. These elusive ghost particles are produced in staggering numbers during the most violent events, like supernova cores collapsing and material accreting onto black holes. They travel across the universe almost completely unimpeded, carrying information directly from the heart of the cataclysm. Gigantic neutrino detectors like Ice Cube buried deep in the Antarctic ice are constantly monitoring the sky. When a fast radio burst alert comes in, physicists scour Ice Cube's data from that exact moment, looking for a statistical bump in neutrinos coming from the same direction. A single high-energy neutrino coinciding with an FRB would be a landmark discovery. It would tell us that the engine behind the burst was not just magnetically violent, but also an incredibly powerful particle accelerator, a place where protons and electrons are being whipped to nearly the speed of light. This would provide crucial details about the physics happening in the immediate vicinity of the magnetar or black hole, details that are completely hidden from our view in the radio band alone. Every non-detection is also valuable, ruling out certain classes of models that predict bright, high-energy counterparts. The multi-messenger hunt for fast radio bursts is a painstaking, global game of cosmic correlation, where every flash in the dark is a potential clue, and the collaboration of the entire astronomical community is our best hope for finally turning these brilliant mysteries into well-understood chapters of the universe's grand narrative. And as we stand on the precipice of this new era of discovery, the future of hunting these cosmic signals is poised for a revolution so profound it will render our current efforts a mere prelude. The key to this transformation lies not just in building bigger telescopes, but in constructing an entirely new kind of instrument, one with a collective ear so sensitive it could hear the whisper of a radio wave from the edge of the observable universe. This is the ambition of the Square Kilometre Array, the SKA, an international mega project that will be the largest and most advanced radio observatory ever built. Unlike a single massive dish, the SKA will be a vast network of hundreds of thousands of individual radio antennas spread across remote locations in South Africa and Western Australia. Its name comes from its total signal collecting area, which will eventually span over 1 square kilometre, giving it an almost supernatural ability to detect the faintest of cosmic whispers. The impact of this new tool on the study of fast radio bursts will be nothing short of explosive. Where current powerhouse telescopes like CHIME are now detecting bursts by the thousands per year, the SK is projected to discover them by the thousands per day. Imagine that for a moment. We will move from a data stream to a data tsunami, collecting more FRBS in a single week than we have in the entire history of their study up to this point. This isn't just an incremental improvement, it's a fundamental shift in the scientific paradigm. We will no longer be limited to studying a few dozen well-localized, well-studied bursts. We will have a statistical population so vast that we can finally begin to see the true taxonomy of these events. We will be able to identify subclasses that are currently invisible to us, finding the cosmic oddballs and the rare one in a million events that could hold the key to understanding the entire phenomenon. Are there bursts that only occur in galaxies of a specific metallicity? Are there repeaters with periods of years or even decades that have simply eluded our limited observing time? The SKA will find them. This unprecedented deluge of data will allow scientists to do something they can only dream of today: use FRBS as high-precision cosmological probes on an industrial scale. With tens of thousands of bursts pinpointed to their host galaxies, each one providing a measurement of the cosmic web's density along its specific path, we will be able to construct a stunningly detailed three-dimensional map of the universe's missing ordinary matter. This map will reveal the fine-scale structure of the warm-hot intergalactic medium, showing us the cosmic filaments and voids in a level of detail that will test our best models of the universe's large-scale structure. Furthermore, the sheer volume of bursts will allow for a technique known as cosmic tomography. By analyzing how signals from the same source, but arriving at slightly different times, are affected by the drifting interstellar plasma of our own Milky Way, we could even map the turbulent magnetic fields within our own galaxy in incredible detail, using the entire cosmos as a backdrop. But perhaps the most thrilling prospect is the potential to finally catch a fast radio burst in the act of being born, with an unprecedented level of detail. The SKA's incredible sensitivity and its ability to see the sky in multiple directions simultaneously mean it won't just detect the burst itself. It will capture its entire radio fingerprint with a clarity we've never had before. It will see the intricate millisecond by millisecond evolution of the signal's polarization, potentially revealing the precise dynamics of a magnetar's crust snapping or the geometry of a jet from a supermassive black hole. Its wide field of view also makes it the perfect trigger for the global multi-messenger network we discussed earlier. When the SKA detects a burst, its instant alert will be so precise that every major optical, X-ray, and gamma-ray telescope on Earth and in space will know exactly where to look, dramatically increasing our chances of catching that fleeting, multi-wavelength counterpart that would definitively identify the engine. With this kind of power, the long-standing mystery of what creates the majority of fast radio bursts could very well be solved within the next decade, turning one of the greatest enigmas in modern astronomy into a standard tool for exploring the cosmos, a routine beacon illuminating the dark. And so, after this incredible journey through 30 of the cosmos's most puzzling signals, from the first lonely Lorimer burst to the hyperactive chattering of repeaters embedded in their own glowing nebulas, we arrive at a conclusion that is, in its own way, as profound as any single discovery. There is no single, simple answer. The quest for a lone silver bullet explanation, one cosmic engine that could account for every last flash and flicker, has quietly given way to a far richer and more complex reality. The true story of fast radio bursts is not a mystery with one solution, but a grand cosmic tapestry woven from many different threads. The evidence we've gathered points irresistibly toward a universe that is wildly creative, possessing not just one, but an entire arsenal of ways to generate these brilliant, fleeting shouts in the dark. We are not studying one type of phenomenon. We are witnessing the signatures of a diverse population of cosmic sources, each with its own unique personality and life story. Think back to the clear distinctions we've observed. On one hand, we have the persistent repeaters, objects like FRB 121102, which fire off bursts in an erratic, staccato rhythm for years on end. These are not objects that destroy themselves. They are engines with longevity, with a persistent power source. The evidence for these strongly points to young, hyperactive magnetars, neutron stars with magnetic fields of almost unimaginable intensity, born in the chaotic stellar nurseries of dwarf galaxies. These celestial toddlers are prone to violent tantrums, their solid crusts cracking under magnetic strain in starquakes, or perhaps being pelted by debris from their own birth, as in the dramatic dragon model. They are the steady, though unpredictable, arsonists of the cosmos, able to light the same fire again and again. This class of bursts represents one distinct population, the survivors, the long-lived volatile objects that provide a recurring laboratory for us to study. Then, in stark contrast, we have the vast majority of signals, the one-off bursts. These are the true cosmic ghosts, screaming into existence from a random point in the sky and then vanishing forever into absolute silence. Their very nature, their one-and-done character, is the most important clue we have. It tells us that the event that caused them was so profoundly catastrophic that the source was completely and utterly obliterated. This is the domain of the final, irreversible cosmic disasters. Here, the leading suspects are the spectacular mergers of two neutron stars, collisions that unleash gravitational waves and forge heavy elements like gold, and in their final, chaotic moments, might also whip up a magnetic maelstrom capable of launching a single, brilliant radio burst before collapsing into a black hole. Or, even more exotically, the Blitzar, a massive neutron star living on borrowed time, its rotation finally slowing to a critical point where it collapses into a black hole in a millisecond, its magnetic field severed and imploding in a final, coherent blast of radio energy. These one-off bursts represent a second, separate population, the self-destructing systems, the grand finales of stellar lives. And the plot thickens further when we consider the outliers, the signals that refuse to fit neatly into either box. The repeater found in the ancient globular cluster of galaxy M81 shattered the assumption that all magnetars must be young. It forced us to invent new cosmic pathways, like the slow, patient merger of two white dwarfs billions of years after star formation ended, creating a magnetar in a stellar retirement home. The bursts with inexplicably high dispersion measures might be whispers from the universe's infancy, while the signal co-located with a persistent radio source painted a vivid picture of a newborn magnetar still swaddled in the hot shroud of its supernova remnant. And we cannot entirely dismiss the more speculative yet physically possible explanations. The collapse of a dark matter action star near a neutron star, or the snapping of a primordial cosmic string, a defect in spacetime itself. These rarities suggest there may be a third, even more exotic population at play, reminding us that our catalogs are still young and that the next detection could always be the one that breaks all the rules. This grand synthesis, this acceptance of a mixed population, is not a scientific failure or a cop-out. It is, in fact, a sign of a field maturing beautifully. It reflects a deeper understanding of how the universe operates. We don't look at all the stars in the sky and demand a single explanation for their varied colors, sizes, and life cycles. We recognize red giants, white dwarfs, and main sequence stars as different stages of stellar evolution. In the same way, we are now learning to see fast radio bursts not as a single puzzle, but as a common, observable effect produced by several of the most extreme and energetic processes the universe has to offer. The true unifying theory of fast radio bursts is not a specific physical mechanism, but a broader principle, that the cosmos possesses a remarkable plurality of methods to generate coherent, intense flashes of radio light. It is this very diversity that makes the field so endlessly rich, so challenging, and so thrilling. Every new detection is no longer just another flash. It is a new data point that helps us classify and understand the different species in this brilliant cosmic ecosystem, reminding us that the universe's imagination is far, far greater than our own. So, after this breathtaking voyage across the cosmos, from that first lonely pulse found in archival data to the thousands of bursts now flooding in from observatories like CHIME, what have we truly learned? We began with a single, unexplained flash and have since uncovered a universe teeming with them, each one a unique cosmic character. We've met the silent, one-off ghosts that scream and vanish forever, likely the final death cries of colliding neutron stars or collapsing blitzars. We've been introduced to the erratic repeaters, the volatile chatterboxes like FRB 121102, which point so compellingly to the immense power of magnetars, neutron stars with magnetic personalities. We've even encountered signals from utterly unexpected places like ancient globular clusters, forcing us to invent new stories of stellar resurrection and patient billion-year-old mergers. The evidence is clear. There is no single, simple answer. The universe is not so monotonous as to have only one way to shout. Instead, we are witnessing a diverse population of cosmic engines, a brilliant menagerie of celestial phenomena that all share the same spectacular final product. A fleeting, powerful flash of radio light that captures our imagination and challenges our understanding. The journey itself has been as remarkable as the discoveries. We've evolved from a handful of puzzling anomalies to a rich field of statistical science, using these bursts not just as objects of mystery, but as tools to map the invisible cosmic web and weigh the universe's missing matter. We've built a global network of telescopes that work in perfect harmony, instantly alerting each other to chase down these ephemeral flashes across the entire spectrum of light. And through it all, the magnetar has emerged as a leading protagonist in this cosmic drama, with the detection of a burst from within our own galaxy serving as a powerful confirmation that we are on the right track. Yet, for every question answered, a new, more fascinating one emerges. The existence of periodic repeaters hints at intricate binary dances, while signals with extreme dispersion measures may be carrying secrets from the universe's first billion years. The door remains wide open for more exotic explanations, from the collapse of dark matter action stars to the snapping of cosmic strings relics from the very birth of spacetime. This is not the end of the story, it is the end of the beginning. The greatest takeaway from our exploration of these 30 signals is not a definitive solution, but a profound appreciation for the dynamic, creative, and often violent universe we inhabit. The mystery is not yet fully solved, and that is the most exciting part. It means the next great discovery is still out there, waiting. With monumental projects like the Square Kilometre Array on the horizon, poised to detect thousands of bursts every single day, we stand at the threshold of a new era. The static of the cosmos is slowly being transformed into a symphony, and we are only just learning to listen to its most dramatic movements. So, the next time you find yourself looking up at a clear night sky, remember this: in the silent spaces between the stars, a brilliant conversation is happening. It's a conversation of colliding stellar corpses, of magnetic monsters having tantrums, and of forces so fundamental they shape reality itself. And all it takes is a radio telescope pointed in just the right direction at just the right moment for us to hear the next incredible chapter. We want to hear your thoughts on this cosmic detective story. Which of these theories captures your imagination the most? Do you think we're listening to the final cries of dying stars, or could there be something even more incredible behind these signals? Share your favorite idea in the comments below, and if you've enjoyed this journey to the edge of our understanding, be sure to subscribe. There are countless more secrets waiting to be uncovered, and we'll be here to explore them all.